Hello and welcome to my next session in my Data Science with Mathematica series. Today I will be talking about dynamic programming. That is a very important topic for the data scientist. It is very important in mathematics, in combinatorial optimization. It is very important in operations research and its many application areas. Production scheduling, all sorts of logistics tasks. We need dynamic programming in pretty much all areas of operations research, and therefore it's also relevant for the data scientist. Very often the data scientist needs to model certain problems with dynamic programming in order to be code efficient and harness many of the other advantages of dynamic programming that I will be talking about today. So I will start with a general introduction to DP. I will first talk a little bit about the name, where the name comes from, and why there are some curious things about the name to begin with. Then I will point out and demonstrate that the prototypical example of dynamic programming is shortest path, and also in its complementary version, longest path. I will then talk about the basics of DP in general. There's much more to be said about DP than just shortest path, but we need to have an initial understanding of the modeling of a shortest path problem. We need specifically a topological ordering. That is a prerequisite, and I will introduce that. And then I will provide several examples from easy to harder, from shortest path to not shortest path. So there are two ways to model or to iterate about the different states of a DP problem. They're called recursive fixing. This is basically the indices from the end to the beginning, also called backwards termination, and several other words are available for that, as well as reaching. And in reaching, we start at the source and go to the sink. In recursive fixing, we start at the sink and go backwards to the source. We can easily minimize with the maximization version, and we can easily maximize with the minimization version. That is oftentimes quite useful because sometimes maximization is more efficient than minimization, and vice versa. But we may have a maximization problem, and if then minimization is more efficient, we want to do minimization, but we have to flip a couple of signs in order to be able to maximize with a minimization. Then I will show that we can oftentimes transform many problems to shortest or longest path, and then use the simplicity of DP when applied to a shortest path problem. And then I will talk a bit more detailed about how to cope with multiple optimal solutions. Very often you're only interested in one optimal solution and you're okay with that. But if there are multiple solutions, well, then sometimes a corporation would like to know what all these optimal solutions are. It's entirely possible that the company may have secondary concerns that would allow a company to choose from the multiple solutions that are more aligned with a secondary concern, because we cannot always model everything as a primary concern in our model building. Then we look at ways to find all of them. I will then talk about several applications of DP, and that is a very long list. And then I will provide some final comments. Okay, so let's jump right into it. Let's first talk about a little bit about the name. The inventor is sometimes considered Richard Bellman. By some, he's considered the inventor of combinatorial optimization, and he coined the term back in the 1940s. Back then, the word dynamic meant that things change over time. We still have that meaning of dynamic today. He used that term as it reflected the nature of performing optimization in multiple stages, and that's a very important thing to recognize. we are performing optimization over multiple stages or states, and there's going to be a difference between the two. So when we look closely, then DP performs multi-stage optimization, where several stages have to be computed to obtain the desired solution in the last step. And the last step can be at the end and it can be at the beginning. So a certain hierarchy is needed, as the desired solution in the last step is embedded in a more general problem, and that's one of the characteristics of a DP problem. We are embedding a problem in another problem, and every state corresponds to an embedding as we are moving from start to end or from the end to the start. And then the problem in every stage is itself embedded in a larger problem, and that's why problem embedding is a key feature of DP. And that means several stages have to be solved one at a time successively, and that's why Bellman used the term dynamic. And also in his belief, the word dynamic also sounded impressive. And the word programming was simply used in the sense of optimization, and in particular in Britain, programming had an optimization meaning. And we still have that somewhat today. It referred to the use of the method to find an optimal program in the sense of a military schedule for training or logistics. So this usage is the same as that in the phrase linear programming or Mathematica program. It's a synonym for mathematical optimization. We still have that today. And here I give you a hyperlink where you can find more about Richard Bellman. And there's a little bit of a game to that name, and I do give you a quote from his autobiography. I'm not going to read it to you right now. The basics is that Bellman tried to avoid the word research for certain political reasons. The Secretary of Defense in the United States back then hated that word, and it was important for him to avoid the word research. So I'm not going to read it now. Please stop the video or download the notebook. So here's a link about the history of dynamic programming, and for more background on the several names that Bellman has given to dynamic programming, here are two links about the PDF that I think is quite definitive about where the name dynamic programming comes from. Okay, so now let's look at shortest path as a prototypical example for DP. So it is the shortest path in acyclic networks, and that is because it is rather intuitive, visual, and a starting point for several improvements based on combinatorics and graph theory. So we'll start out with shortest path here. It is a very simple yet powerful prototypical example for DP, but we will then later also look at several other things where we don't have a shortest path representation. So the objective is not a shortest path itself, but the problem transformation to a shortest path allows DP to solve it. And many real-life problems can be modeled as a shortest path problem. Many combinatorial problems can be transformed or reduced to shortest path or longest path. And the objective is not really comprehensible sometimes as a shortest path, but with proper definition of the recursion and proper initialization, the problem can easily be solved with DP. So definitely not all DP problems are shortest path problems. DP is a very general framework because it's based on recursion and induction, which makes it incredibly powerful in general, but by no means is it restricted to shortest or longest path. So we have to make an assumption. We have to assume we have an acyclic graph. So negative arc lengths would actually be permitted for shortest path, but no negative cycles. And that, I think, is also pretty intuitive, pretty clear, because otherwise we would simply cycle over the negative arcs and our objective function would go lower and lower and lower, right? We want to minimize something, but we can always drive it down to minus infinity by going in circles. Well, that's not quite sensible, and therefore we have to rule out that our graph has negative cycles. Otherwise we can simply create an infinite loop and cycle to minus infinity. In the case of a maximization problem, we could cycle towards infinity. But that's really not too much of a restriction for the following reasons. In many applications, the node represent calendar times, and the arcs represent increases in calendar time. So the graph is necessarily acyclic, because a cycle would entail time reversals, and humanity is not quite able to do that yet. And in acyclic networks, the shortest path or longest path problems are interchangeable. Either can be converted into the respective other simply by multiplying the arc lengths with -1, and I'll show more about that below. Dynamic programming is also sometimes called recursive optimization, and I think that is a very good name for this. We are relieving ourselves from this legacy terminology. Recursive optimization, I think, hits the nail on the head, because we're performing recursion at every step in the embedding and every step in every state, and we apply an optimization objective function in every step. And I think recursive optimization is, in my personal opinion, the best name for this. And that describes the essence of the mechanisms that I think hit it better than dynamic programming. So with DP, we have the following three items that are very closely related concepts. We have dynamic programming, induction, and recursion. And induction and recursion are very clear mathematical concepts. And when we bring them together with an optimization function, we get dynamic programming. And please take this as a rotatable triangle. I don't mean to imply a hierarchy here, but to show a triangle, I have to somehow show a hierarchy. But I don't mean to imply one here. These are all separate but related concepts, and it's not that dynamic programming is on top of the other two. So everyone is an extremely powerful concept on its own, and every mathematician or data scientist needs to be thoroughly familiar with them, each and every one of them on their own. And if you add an objective function and boundedness to recursion, you get a DP. And if you add convergence and boundedness to induction, you get DP. And recursion itself is based on induction, and it is oftentimes proved with induction. And induction is a recursive process, so we see that all three of them are very closely related. I'd like to make a short excursion. There is an add-on package called Mathematica, written by a very ingenious programmer, and I would like to endorse Mathematica at this point. It's written by Szabolcs Horváth, and you can see this a lot in all my Mathematica notebooks in the future. With Mathematica, you can use your local tech or LaTeX installation. You can use these commands directly from your Mathematica session. And you can use typeset for output. For example, here we have that. And you can also display Mathematica expressions on their own in tech and then show it with Mathematica. Right? So here you see basically tech markup language. Right? This is basically, tech is a markup language, and you can use that, or you can use Mathematica expressions directly. The input to Mathematica can be either one of them. You can even use color in your code, and that simply requires you to add the color package in the preamble to the expression that you're submitting. And note that I now have both X highlighted in red. So the result is a Mathematica graphics expression, so you can do pretty much anything you want, as you could with any other graphics expression, including copy-paste into a text cell. A lot of output I know would copy-paste and put it into a text cell in the middle of the text where I want to show a formula, right? It's really just a graphics expression. If we look at the full form of it, we are getting a big graphics expression. You can see that the head is graphics. Okay, so I think this merely scrapes at the surface in terms of the features of Mathematica, It also comes with help browser integration and contains, I think, very well chosen examples. And I have put a needs of the Mathematica package in my init.m, so it loads every time the kernel is started or restarted, so I always have it. So, short version, get it. You need a working tech installation on your computer, but as a data scientist, you should have that anyway. At a minimum, all you need is Tech Live, along with the Tech Live standalone edition. But you can also use others. A LaTeX installation or AMS LaTeX installation should also work, but you do need the standalone edition. And here's a hyperlink. Okay, with that, let's jump into the basics and the characteristics of dynamic programming. The crucial element in DP is a principle that is variously known as the principle of optimality, or more specifically, the Bellman equations, and there are several flavors of that. That's why I personally prefer the name principle of optimality, because what that means in a particular case for the Bellman equation can be very different manifestations of the Bellman equation, and I'm going to show you a few choices. It's also called a functional equation, and I think that is not necessarily the best terminology. In a strict sense, it does meet the requirements of a functional equation, but I think the term is perhaps misleading. It's also called discrete optimization over states, and sometimes states are grouped into stages, and embedding, sometimes called optimal substructure property. Right? We need recursively optimal substructures in order to get DP to work. So the characteristics of DP are the following. The problem can be divided into states, and every state represents a decision that we are doing, we are performing at that stage. Should we go to the right? Should we go to the left? Should we take the higher value? Should we take the lower value? So a state is basically a decision point, and sometimes states are grouped into stages. The decision at one state transforms that state into another state. Right? We're doing that through the nesting of the embeddings. Given the current state, the optimal decision for each of the remaining states does not depend on the previous states or decisions. So every state is a new decision based on the knowledge that is inherent in the incoming data. Right? In the recursion, we always use a certain manipulation of something that's coming in from previous computations that were done with the embedding in optimal substructures. And this may remind you of the Markov property. Right? In Markov theory, we need one state to be independent of all the previous states. And there is a whole class of DP problems that deal with Markov problems. And they're called the Markov dynamic programming problems, or MDPs. Right? This is very important that we see the link here between the Markov property and the independence of previous states in dynamic programming. So next, there exists a recursive relationship that identifies the optimal decision for state J, given that state J plus 1 or J minus 1, again, depending on if we go upward or downward, forward or backward, has already been solved to optimality. Right? That's the optimal substructure property. And the final state, or the first state, must be solvable by itself. Right? In induction, that would be called the induction anchor. We need to throw an anchor where we want to start with the induction, or where we want to start with the recursion. And the last 2 points make it a recursive problem. And again, note the similarity to induction. Right? Induction inherently relies on having an anchor and then use recursion on it. So I had already mentioned, in order for this to work, we need to have a topological ordering on our nodes. We have to emphasize that this is absolutely important. We need it. That means every arc from I to j has always I less than j. This is important that we have this ordering in our network structure. If our graph doesn't have that already, we have to convert it into that shape. And this can easily be done in O of n time, in other words, in linear time. It is quite easy and intuitive to perform such a relabeling. At worst, you can do a search algorithm. If you can do search, then you can convert into topological ordering in linear time. Okay, so I will leave that out at this point. Such transformations should be pretty trivial. We can always do it with a search algorithm, or in the network, we already do it in a topological ordering from the beginning. So that also means that if we have a cycle, this is not possible. For example, how are we supposed to model a topological ordering with this graph? We have an arc back from 4 to 1, so we have a cycle here, right? One cycle would be 1 to 4 and back. Another one would be 1, 3, 2, 4 and back. So here we have 2 cycles. And in order for a topological ordering to be possible, we need a graph that has no cycles. And you see that here this graph is cycle free. And you can easily relabel that in the following manner. In an acyclic network, there must be exactly one and only one node that has no incoming arc. That is this one here at the top, right? You see it has 3 outgoing arcs, it has no incoming arc. So make that node number 1 and then delete it along with all the arcs emanating from it. So then you're left with those 3 here at the bottom row. You now have the same situation as before. There exists exactly one node that has no incoming arc. So in this case, it would be the one here at the lower left. That if you remove the first one along with these 3 outgoing arcs, then this one here in the lower left has no incoming arc. So now that is going to be the next one, right? Proceed in the same manner. Delete it along with all outgoing arcs, call it node number 2, and in the spirit of this session you already see the recursive nature here, right? The next one would be this node here that you delete, and then you're arriving at the terminal node. Okay, at the end there's only one thing left, and it will get the label n, the last one. Right, so in the example above we could easily remove the node at the top along with all outgoing arcs. It has no incoming arc, so that will become node number 1, and so forth. You do it with all the other nodes that are remaining. And if you don't have any node that has no incoming arc, then you have a problem because you have a cycle, right? When nothing is there without an incoming arc, there's always an incoming arc coming from somewhere, and that means there is a cycle. Okay, so let's look at a few simple examples. So in the following, we assume that all nodes have a topological ordering. I will not further mention that in detail. So we have this graph here. I've scanned that from one of my many old books. I model it as a net here, and then let's look at it. We have this node structure here in this graph representation. You see that it's the same as we have here in this scan. And let's make a couple of definitions. Fi is the minimum travel time from node I to node 9, and 9 is the last node here. So by definition, F9 is 0, right? Because we have no more outgoing arcs there. There is no cost arc that emanates from F9. So it's pretty much by definition that we have F9 is 0. And Ti is now the travel time along arc of ij. For example, T47 is 15 because in the arc from 4 to 7 we have a 15 here. You see this arc from 4 to 7 we have a 15. And it's important to note that in a cost minimization problem, sometimes it's called time that we're trying to minimize, sometimes it's cost, sometimes it's another item of burden or inefficiency or whatever, right? These are all cost dimensions, and sometimes cost is measured in currency, sometimes it's measured in time. So I use those things, cost and time, interchangeably. And I use rectangle shapes on the nodes when I show a new graph that we haven't worked with yet, when I introduce a new problem. So We can now interpret this as fj plus tij as the travel time of the path from node I to node 9. So that traverses arc ij and then travels as quickly as possible from node j to node 9. So this property, as quickly as possible, that is already fully captured in f. F is by definition, by design, the optimal route, and that's why it also has only one index, because the optimal route now starts from a node, whereas the arc needs two indices from 2, right? ij are from 2 arc, are the nodes that specify from and to. But for a given node, we have that index and they are in topological ordering. And the property as quickly as possible or as cheap as possible is captured in the nature of f itself. All right, this is important to realize. This is a path from node I to 9. So its travel time must be at least as large as fi. In other words, we have this inequality. So the optimal path from node I to the end, which is node number 9 in this case, is less than the optimal distance from node j plus the costs to get from I to j. Right? You can probably see the triangle inequality here. But it's important to realize that fi would now be optimal. We're doing this over all the I. It just can't be 9 because that's our end. And this triangle inequality, like modeling, shows us that this is in a way the definition of the optimum for fi. It's the best solution. When we do this over all the I, you can't get any lower. fi is the shortest path from I to the end node. But the fastest path from node I to 9 traverses some arc ij first, and then it gets from node j to node 9 as quickly as possible. So some j satisfies the displaced inequality with an equality, and in that case we have the optimum as I just mentioned. Our fi is a minimum. We just have to go over all the j, and the j are the nodes that are the end nodes after leaving I, because tij goes from I to j. Right? So when we have a fixed node, we look at all the outgoing arcs, and those are the j's, and we take the minimum for them. That makes fi the minimum, and we have a new shortest path from I to the end. And we found it by minimizing over the costs that are already minimum for all the nodes that follow I plus their traversal times. Okay, so again, note the recursions here, that fi on the left side depends on fj on the right side. We have that in the inequality and in the equation. Right? Note the recursion here. This is important. So in the following, let's look at the shortest path itself for our example, and we go from the sink to the source. So we do recursive fixing or we do backwards termination. And when we look at this, and for comparison, let's look at the network graph again. I will use my window tools that I have presented in my J-Link session. So I sometimes, for comparison, instead of always scrolling up and down, I just like to have a window with an expression next to it. And for that reason, I have to find a window function that has the always on top property set. So let's run this with JW, and this gives me this new window here, and it's always on top, and I like to keep it there because now I can scroll the notebook and I keep the window right next to it, on top of it. So we start at node 9, and we had already said that node 9 has an f value of 0. It has no outgoing arcs. It's the sink of this network. So the next one then, due to topological ordering, we can take the next lower number. That would be 8. And f8 is 10 plus f9, right? There is only one arc and therefore only one path from 8 to 9. So the value has to be 10. We don't have any alternatives here. So we store this in memory. f8 is 10. The next one is f7. And we can see that f7 also has only one outgoing arc, and it goes directly into the 9. So for f7 it's equally trivial. We take 3 plus f9, and that is 3. But next one is f6, and here we say that we have two choices. In order to get from 6 to 9, we can go either direct at a cost of 15, or we go via 8, then to the 9 at a cost of 17, because we need 7 plus 10 in order to get to the 9. So these are our two choices here. It's 7 plus f8, or it's 15 plus f9. And the minimum of those is the 15. So going from 6 to 9 directly is cheaper than going from 6 to 9 via 8, because that would be 17. f5 now is also relatively easy. It has only one outgoing arc. So f5 is 7 plus f7, and that is 10, because we have 3 from f7. We had computed that here. Plus we have the traversal time from 5 to 7, which is 7. So we have 7 plus f7, and that is 10. All right, another one that's stored in memory. And I hope you get the feel for the fact that all the f's are already optimal paths, right? When we stop here at f5, then all our numbers, f9, f8, f7, f6, f5, they are already optimal by design, right? And that's a property that we have to rely on. Now f4 is getting a bit more interesting. We have 4 outgoing arcs from f4, 4, 15, 7, and 3. So we have to pick the minimum of 4 plus f5, that would be this arc, 15 plus f7, that would be 4 to 7 with 15 plus the optimal path from 7, 7 plus f8, so we go from 4 to 8 with the cost of 7 plus f8, and we have the choice 3 plus f6, so we go from 4 to 6 at a cost of 3 plus the optimal path from 6 to 9. And the optimal value here turns out to be 14, and that 14 is 4 to 5 to 7 to 9. Everything else is more expensive. 15 costs more, 7 plus 10 is more, and 3 plus 15 is more. So the shortest path from 4 to 9 is 4, 5, 7, 9, because that's 4 plus 7 plus 3. Alright, and in this manner we continue until we arrive at f1, which gives us a total value of 19. And what we just did here manually, we can now put into a do loop. We start at the sync minus 1, right? We know that f of sync is 0, so the first one in the loop is going to have to be f8, so that is sync minus 1. And we go all the way down to the source, that would be node 1. And we do that by always taking the minimum of, and this is the recursive formula. Net of the lookup is our cost t, right? This is cost t of ij plus the f value, which by design is already minimal, right? And we always restrict it from all the keys of net that we have to be count to be the originating node, right? We're on the left side here. This represents our I, and the number that we are looking up with the cases would be the j. So we do this with the cases of all of them, and we have the count on the left side. That's important to realize for recursive fixing, because in a moment we're going to be doing reaching where this is reversed, right? So we're looking at the outgoing arcs where we have the originating node and looking up for the outgoing arcs. So when we do this, then we have these optimal numbers. 9 is 0, we knew that before. 8 is 10, that matches what we have computed here, that's our 10 at the beginning. 7 is 3, 6 is 15, that's what we had up here, and so forth, all the way until the 1 is 19. We have that down here in the last row. Okay, so a simple do loop, and I had already mentioned that this is a fairly simple operation, quite straightforward in how we can write dynamic programming with simple recursion in a very code-efficient manner. And as a side effect, this method also gives us the entire tree of shortest paths, right? Not just one. We're not just interested in F1. That may have been our primary interest. But what if we want to know the shortest path, for example, from node number 5? We already know it's 10. We have already computed it. What if I want to know the shortest path from node number 2? Well, it's 20. We have computed it, or from 4. So we are getting a tree of all the shortest path values. All we have to do is store all these minimal segment values in a tree, right? And I think this makes it very easy to understand. And let's generate this by also storing the nodes themselves. So I introduce another variable here, tree, in which I append to that variable with that solution. So let's compute that and create a graphics grid of the tree solution. And we see that we have this optimal path tree here on the left. And I've also inserted that very tree in the entire network and highlighted the tree with red arrows. So you can see that this tree here on the left corresponds to the tree in the scan. So let's also do a JW of G1 for comparison. Let's scroll back here and you see that they correspond. It's the same tree. It's the same tree left to right in the scan, and we have top to down in this Mathematica tree, and we see that they are identical, same shape and the same values and the same arc values. And we have this in the entire tree with the shortest path tree embedded as red arcs in the right tree. That's sometimes easier to understand in the overall picture, but at the end of the day, we are really interested just in the shortest path tree. The entire tree can be pretty confusing, and we're going to see this for larger examples later on. We're really interested in the shortest path tree on the left. That is really the representation of the optimal solution, and usually for that we don't need the entire graph. Okay, so in the example above, to get from home to office via the shortest road, it turned out to be the easiest to solve the problem by embedding it into the more general problem of finding the shortest path from each node to the office. That is node 9. Right? And a short footnote, this approach would even work for cyclic networks as long as it doesn't have any negative cycles in it. Right? Sometimes in DP it can be forgiving for cycles as long as they're not negative. So some important things to note here. We never branch out from any node. We can see that in the optimal shortest path tree on the left, every node only has one and exactly one outgoing arc. We never have multiple outgoing arcs. We may have multiple incoming arcs. 4, for example, has 2 incoming arcs and 9 has 3, but we never have multiple outgoing arcs. Every node has one and exactly one outgoing arc. Yeah, we only converge to join or flow into nodes. I'd call it branching in if that expression were to exist. Every node has exactly one outgoing arc, not 2, not 0, it's exactly 1 except for the final node. All nodes have incoming arcs, so there's also no node that's missing an incoming arc, except for when we start in the tree. So this means we can take any node as a starting point for the question, what's the shortest path from that node to the sink? We can read it off directly from the shortest path tree. This one here on the left. And in other words, the shortest path tree generated with recursive fixing does not only contain the optimal answer for the source, that was node 1, but for all the nodes as starting points. Another thing, that we can never get stuck in a dead end. We never have the case that we couldn't determine the shortest path from any node as a starting point. Every node has exactly one and only one red outgoing arc. Alright, there may be more outgoing arcs, but only one can be red. It's the optimal shortest path. So that bullet point refers to the network on the right. Every node has exactly one outgoing red arc. It may have multiple incoming arcs. So, and in terms of runtime, we're also quite efficient. We need to look at every arc exactly once, because every arc could be on the shortest path, so we have to at least examine it, we have to at least look at it. But we don't need more than that due to the efficient tree structure. And that means our runtime is O of m, and that means linear. And this is very good news. This is great news in combinatorial optimization. Many problems are O of n squared, n cubed, or exponential. So in combinatorial optimization, when you've got a linear solution, then you've got it pretty good. So for the purists among you, I have to say, strictly speaking, the problem is only pseudo-polynomial, because we are not polynomial in the input size of the data. If the data is so big that we cannot store it in 64-bit arithmetic, then the problem does become exponential again. But for our practical purposes, we're linear. For reasons of being totally correct, I have to say the problem is only pseudo-polynomial, because we don't say anything the input size of the data. But good news, no other algorithm for solving shortest path on an acyclic network could be better than O of m. It is the worst case complexity, because we need to look at every arc at least once, which in itself takes O of m time. So we can't get any better than O of m. So next, we can also go in the opposite direction from the source to the sink. Why do we have to go from the end to the beginning? How about we go from the beginning to the end? It works similar in principle. We just have to change the indices of the loop structure. It's easy to flip this around. You can think of this as forwards termination. And it's also sometimes called the reaching method, because we reach out from every node. Instead of looking at incoming arcs, we're now looking at our outgoing arcs. So we are reaching out. That's where the name comes from. So if we now want to look at the shortest path, but we go from the source to the sink and do this with reaching, then we have to say that our source is 1, our sink is 9. We had that before, but we have to make the following little changes. We now have to say f of source is 0. For recursive fixing, it was f of sink was 0. We now have to say our optimal f value of 0 has to be at the source. We flip around the indices. Instead of going from sink -1 to source, we go from source +1 to sink. And look carefully that we are now having count on the right side in the sublist in the cases, and we have the pattern matcher on the left. So we have basically flipped around the order here. We need that because now we are reaching out from the originating node of the arc to all the next nodes that represent the ends of the arc, which is exactly the other way around. And we also have to flip the index here. We now need f of hash of 1, and it was of 2 for recursive fixing. So this is really the only change that we need to do. We need to initialize at the source, not at the sink. We need to flip around the indices. We need to change the iteration order, and that's really it. And when we look at the graph structure here, we're getting the very same output, but now the labeling is the other way around. So we start at 1 with 0, that's what we defined as the initialization, and then now our optimal path is 1, 3, 4, 5, 7, 9, and we have the 19 at the 9. right? And it's the same graph that we had before here in our entire graph, where we are embedding in red the optimal tree. So important to note here, we have several things done exactly the opposite of what we saw in recursive fixing. This time we do branch out from the nodes here. So we can clearly see here that every node has only one incoming arc, but it may have multiple outgoing arcs. So for example, when we look at 3, we have 2 outgoing arcs. And when we look at 4, we have 2 outgoing arcs, right? But nobody has more than one incoming arc. Every node has exactly one incoming arc, not 2, not 0, exactly 1. And not all nodes have outgoing arcs. And you see that, for example, here in 2 and 6 and 8. They all have incoming arcs, exactly 1, but no outgoing arc. So here we can get stuck on the question, what's the shortest path from this node j to the sink? Here it's entirely possible. For example, with the 2, we have no path to the 9. From the 6, we have no optimal path to the 9. From the 8, we have no optimal path to the 9. But here we never get stuck on the question, what's the shortest path from the source node to the node j? We always have a red path from the source node to any other node. So we can always get an answer to the question, what's the minimum distance from the source to that arc? Every node has a red path back to the starting point. We can get from 1 to 5 in optimal time. We can get from 1 to 8 in optimal time. We can get from 1 to 9 in optimal time, but that would be the full path and we often don't need it. We can get from 1 to 6 in optimal time. Right? So every node is reachable with a red arc from the beginning. Here the focus is the beginning. With recursive fixing, it was the end. All right, we always have a red path from the source to any other node. So we can clearly see that the shortest paths of both methods are the same, plots 2 and 4 in this plot down here, but that the shortest path trees are different. Right? I think here we have an important comparison. The shortest path is always 1, 3, 4, 5, 7, and 9. 1, 3, 4, 5, 7, 9. But for everything that's not on the optimal path, on the shortest path, we do have isolated nodes. And they only have outgoing. In the case of recursive fixing, they only have incoming in the case of reaching. And you see that the optimal solution is the same in plots 2 and 4, right? 1, 3, 4, 5, 7, 9, 1, 3, 4, 5, 7, 9. But the other arcs can be different. So in the plot 2, we can see that from every arc, we can find an optimal path to the sink. And in plot 4, we can see every node can be reached with an optimal path from node 1. And we see the correct optimal values. 1 has 19 at the beginning, 1 has 19 at the beginning, 9 has 19 at the end for reaching. Okay, so the conclusion is, if in your computation of the shortest path tree you're interested in the question from any node to the sink, you use recursive fixing. From the source to any other node, you use reaching. And you can read the solutions directly of the resulting shortest path trees thus generated. Right? I think fairly straightforward. So a related problem is the longest path problem. And this is not as crazy as it may seem. For example, for project scheduling or dependency modeling, the critical path modeling would be done with a longest path modeling. The critical path modeling can be done with the longest path method. So for example, imagine you're building a house and you need to build the cellar first. Then the building structure, then comes cabling, then comes painting. And the longest path method tells you the earliest point in time that the house can be finished. So let's take the following interpretation here. Task 2 takes 1 week to complete. And we have that here. Task 2 takes 1 week to complete. So from 1 to 2, we have exactly 1. Right? The cost is 1. So it takes 1 week to complete, and it depends on task 1. Task 3 now takes 2 weeks to complete, because the link from 1 to 3 is 2, right? You see a 2 in here. And it also depends on task 1. Task 4 now depends on task 3. We see that 4 has an incoming up from 3, and that takes 3 weeks to finish after task 3 itself is finished. But task 3 itself has some slack. We can see that 2 plus 3 would be 5, and we have 1 plus 6 being 7. That means we have a little bit of slack here with those 5 weeks. So we could afford up to 2 weeks of a delay without delaying number 4, which shouldn't be delayed because it's on the critical path. We have seen that. So it's not possible to finish 4 before 7 weeks, because we have 1 plus 7 if we go 1 and 2 to 4. The fact that we have 2 plus 3 if we go 1, 3, 4 doesn't really matter for the overall time for task 4. It even means we have some slack there. But 1 to 4 with a cost of 6 should not get delayed. That would delay the overall project timeline. The link between task 1 and 2 is not red, right? We see that up here. So a delay in 1 to 3 of up to 2 weeks could be acceptable, because 1 to 3 is not on the critical path. The task 1 to 4 already takes 7 weeks. However, if task 3 were to get delayed by more than 2 weeks, then the whole critical path would be extended and it would actually change. If this is not 2 plus 3, but suddenly more than 7, then the critical path would not be 1 to 4 and going on, it would be 1 through 4 and going on. The earliest finish date of 27 weeks would no longer be possible, because task 4 would be delayed and task 4 is on the critical path. So the longest path from the source to the sink is the critical path, and any delay on that path would delay the overall project completion date. Delays on other segments are not as critical, however, only up to the maximum exhaustion of that slack. If they take too long, the critical path changes and they become tasks on the critical path now. And in management, the terms CPM and PERT are used for that. CPM is the critical path method, and PERT stands for program or project evaluation and review technique. And they're also used to compute the longest path to determine the critical path. And that's not necessarily done with dynamic programming though, but here in our case, given that it's linear time, it's just the simplest and also most code efficient way to do. So back to our original network. I'm showing it here in no mutilated form. So let's now do longest path sync to source. So sync to source means we do recursive fixing, and for longest path we now need the maximum here. It's important that we are setting this up with a maximum here. It's recursive fixing, so we say f of sync is 0, and what do we get for the value? We get 27. Right? So the longest path here from 1 to 9 has a total length of 27. So let's actually look at the graph itself, and we see that this is the longest path. Right? Let's check out some of the alternatives. If we go from 1 to 4, then 1 plus 6 is the longest way we can do this. If we did 2 and 3, it would not be the longest path. That's why we have red arcs here for 1 to 2 and then from 2 to 4. That is the longest path. And next we have to go from 4 to 6, from 6 to 8, and from 8 to 9. If we did any other way, then it would be shorter, which at this point we don't want. So let's just do a quick check. 4 to 8, for example, that would cost us 7 weeks. But if we go via 6, it would be 10 weeks, because this is 3 and this is 7. Another one from 6 to 9, that would be 17 if we go via 8, and it would only be 15 if we go directly. So Here we see the longest path tree on the left, and we see that we need 27 weeks for that, and is the optimal solution in recursive fixing. Now let's do source to sink, that is reaching. We now get the 27 here at the 9. Let's construct that tree as well. It takes no time, and here is our longest path that we look at with reaching. Again, it is 1, 2, 4, 6, 8, 9. 1, 2, 4, 6, 8, 9. That's exactly what we had here. 1, 2, 4, 6, 8, 9. Right? So reaching and recursive fixing produce the same tree, the same optimal path, although the shortest path trees themselves look different. So let's look at them in comparison. You can see that the longest path trees are not the same. That would be plots 1 and 3. But the longest paths themselves are the same. So we'll be using recursive fixing and reaching a lot, so let's wrap them up in a dedicated function. And func specifies whether we want the shortest path, then we use min, or longest path, then we use max. So here I define recursive fixing and reaching, and we specify source and sink and the function that we want to use. If it's min, then we use minimal by, otherwise it's maximal by. Okay, and I will also use the tree plot and the net plot a lot, so I will also save them up in dedicated functions. Okay, next I want to show that we can maximize with minimum and we can minimize with maximum. So let's use this graph that we had with our 9 nodes, and if we now loop over this with our functions, we can see that when we minimize with min, that was the very first example that we had, we get a minimum path length of 19. You will remember the first one was 19. We can also minimize with min using reaching, and we also get 19. And in the case of maximum length, we can maximize with max using recursive fixing, we can maximize with max using reaching, and in that case we get the 27 we just saw. But we can also maximize with min and minimize with max. So what we have to do here in that case is that we have to flip the signs that we have in our network. Positive numbers have to become negative numbers. But then we also have to flip the sign in the optimal solution, because we would be getting something like minus 27, but it really means plus 27 in our longest path quest. So we have to flip the sign at 2 places. First we have to flip the arc lengths, and then we have to flip the value of the optimal solution. And then we can use recursive fixing with min in order to maximize. We can use recursive fixing with max to minimize. We can use reaching with min in order to maximize, and reaching with max to minimize. And you see that we have these 8 outputs here. Okay, so without further emphasis, we can flip these signs around. Okay, let's go to a somewhat larger example. We have a scan of another network here that is in topological ordering, the way I've defined it here. Let's plot it, and we can now see the layer structure here very well. You can see a layer here in the scan of 3 nodes, 3 nodes here, 3 nodes here, and 4 nodes here. That layer structure is preserved in the plot, and later on such layers will be called stages. I had mentioned at the beginning that we are doing dynamic programming over states, and several states can be grouped into stages. So every layer here would then be called a stage. So let's do shortest path sync to source, and let's plot it, and we get this shortest path tree on the left, and the plot on the right shows you the full graph with the shortest path tree embedded in that full path. And now we want to go in the opposite direction. We want to go from the source to the sink, so we use a reaching, and let's look at that plot, and we have that here. And we can clearly see that we have a lot of branches now that really don't close up to the end. For example, the entire branch 1, 2, 5, 8, 11 doesn't close up because the 5 is so expensive here, right? We can't find an optimal, we can't use the segment 11 to 15 in the optimal path because the 5 is so big. We can get a solution in 11, but the 5 would be way too big for that. If we used 18 plus 5, we would no longer be at 11. So let's compare these 4 side by side. We can clearly see that we have the same optimal path: 1, 4, 7, 9, 12, 15, 1, 4, 7, 9, 12, 15, but we have some dead branches. With reaching, we see that the entire branch 1, 2, 5, 8, 11 is dead. You see there is no red arc here that closes up 11 to the 15. And we can also see in the case of recursive fiction that the branch 15, 14, 10 is kind of dead. 15, 12, 8 is dead. Also 15, 12, 9, and then 5 is dead, right? We can look at 3 and 2, but they're not gonna help. When we look at 3 and 2 here, we can see that they have an optimal path from 2 and 3 with red arcs all the way down to 15, but we cannot close it up with the beginning, with the node number 1, because 5 and 6 cannot be on the optimal path. Okay, so now let's do the longest path. Recursive fixing with max, and we look at the longest path. And we see that we now have a value of 23. The longest path in this one is 23. So here we have an optimal solution of 1, 2, 5, 8, 11, 15. And we see there's a lot of branches that are not optimal if we start at the source. Right? They're optimal if you start there. That's what we saw earlier for recursive fixing. You can start there and go to the end, but then you cannot start at the source node. You can see, for example, that 4 has no incoming red arc, but it has, like all the nodes in the right plot, always one outgoing arc. Okay, longest path, source to sink with reaching, and let's look at this plot here. And again, we have the same optimal path: 1, 2, 5, 8, 11, 12. Right? But the tree shapes are different, right? They are different for recursive fixing and reaching, except for the optimal path. So we see again here entire branches are not used. 4, 6, 10, 13. They're optimal if you start there, but not on the path. And here as well, for example, the branch from 2 to 6 is not gonna end in the end node 15. 2, 6, and then either 9, that's a dead end, or 10, that's not a dead end yet, but then it becomes, after 10 we have 13 and 14, and they're dead ends. Okay? So now let's look at a problem where the solution is not necessarily unique. As long as the path lengths, so from sink to source or from source to sink, it doesn't matter, are the same and optimal. That's important. They have to have the identical value and must both be optimal. We can get actually different solutions. Recursive fixing and reaching can produce entirely different paths. So here we have this graph from a scan. Let's plot our own, and let's look at this structure. So let's look at shortest path, sink to source. That's recursive fixing. Let's compute it. Let's plot it. Okay, so take note of the fact that here we have the optimal path 1, 2, 6, 7, 9, 11. Okay, let's make a note of that because this is going to be important. But now let's do it in the opposite direction. We do shortest path source to sink, that's called reaching. And let's plot that one. And here we have a solution that is 1, 3, 7, 9, 11. And we have a total value of 8 here. We had a total value of 8 here with recursive fixing as well, right? The 1 is 8, the optimal value is in the source for recursive fixing, and with reaching we have the optimal value down here in the sink. So in both cases it's 8. But here our path is 1, 3, 7, 9, 11. But that the shortest path trees are different. I should really change this from shortest path to shortest path lengths. Right? The shortest path lengths, shortest path lengths of both methods are the same, plots 2 and 4, but the shortest path trees are different. Okay? So with recursive fixing we had 1, 2, 6, 7, 9, 11, and with reaching we have 1, 3, 7, 9, 11, but their values are the same. It's 11 in both cases. 11 here and 11 here. So they do produce different results, and also note that in the case of reaching, our path is shorter. We see that the solution is not unique. Both paths 1, 2, 6, 7, 9, 11 and 1, 3, 7, 9, 11 attain the shortest path value of 8, and the second one is even 1 node shorter. It has 5 nodes instead of 6 nodes. Okay, that's important to realize. For the longest path we have no lack of uniqueness here. I'm just showing it for reasons of completeness. There's really nothing interesting to show here for the longest path. They are the same. We have 1, 2, 3, 6, 7, 10. We have 1, 2, 3, 6, 7, 10, 11. Right? So here we have the same paths with the same solution values, but we don't have this in the case of the shortest path problem formulation. Okay, so now let's modify our problems a little bit. So instead of shortest path, how about we revisit our example 1 with some modification. Instead of seeking the shortest path between home and office, we now assume that the arc lengths represent the highest altitudes of their respective segments and thousands of feet among several US cities. And let's assume the driver has an old bad car, pretty beat up, and the engine tends to overheat. So the driver doesn't want to drive over territory that is too high in altitude. We are figuring that climbs will give his beat up car a sterner trial than distance. In other words, he's willing to drive along a distance as long as the highest altitude segment is not too high. Distance is not a problem. High altitude, the climb, specifically it should be the climb to the high altitude, is what's causing the engine to overheat. So the driver wants to find a route for which the maximal altitude is minimal. So we use the same plot that we had before. We use the same network that we had in example 1. Here it is again. And in this case, we don't have to do a lot of modifications. What we're doing now is that we determine the maximum of these two numbers instead of just adding them together. Right? This was net of hash plus f of hash of 2 in our shortest path or longest path formulation. And here we're saying instead of the sum, we're taking the maximum of these two numbers and we're trying to find the minimum of that. We're trying to find the minimum maximum altitude. And we modify this accordingly down here where we're counting the f values. Instead of a sum, we now take the maximum of these two numbers. So let's compute it, let's plot it, and here's our solution. So let's look at this a bit closer. We find that 7,000 feet is the minimal maximum. Because no matter what we do, we have the segment 5 to 7, which is 7,000 feet. So that has to be our optimal value in source node number 1. Because any other path would be at least as high or higher. So if we want to go via any other path, we would get higher. And in this case, it's so simple. We can clearly see that just by looking at the terminal node, any other incoming arc would be at least 10 or 15. So here we would be at least 10,000 feet, could even be higher. We didn't even look further backwards yet. And if we come via 6, it would be at least 15,000 feet. Could be higher, we didn't look back yet. Right? So these are already disqualifying. So the optimal solution here is 1, 2, 4, 5, 7. So the 7,000 here may hurt our driver, but any other path would have segments that would be even higher. Any other segment, we would at least have 10,000 and 15,000 here. So now let's do it with reaching. And here we're getting the same optimal path. Again, we can see 7,000 with reaching. The 7,000 is in the sync node. It's down here at the bottom for the 9. And we see that it's the same path. 1, 3, 4, 5, 7, 9. So when we compare them, we have those 4 together here. However, note another important difference. In the case of reaching, we can get to the node 4 via node number 3. And here we go only 2,000 feet for one segment, and then 3,000 feet for another segment, and then we're in city number 4. In the case of recursive fixing, we go higher. We go 1,000 feet to get to city number 2, and then we have to go 6,000 feet to get to city number 4. So we have different solutions in our optimal path trees. 1, 2, 4, 5, 7, 10 for recursive fixing, and we have 1, 3, 4, 5, 7 for reaching. So these are different optimal path trees, but they both attain the same value of 7,000 feet, and they use the same highest segment, which is 5 to 7. In both cases, we have 5 to 7. We have 5 to 7 here for recursive fixing, and we have 5 to 7 here in reaching. The rest of the trees can look different, but we have this segment in both. So there is no way around this 7,000 feet segment between cities 5 and 7. We see already that we have at least 2 solutions. 1, 2, 4, 5, 7, 9 with recursive fixing, and 1, 3, 4, 5, 7, 9 with reaching. Are there more solutions? So we will answer that question a little further below, where we look at multiple solutions when we have a bit more background on multiple solutions. Another example for reducing a problem to shortest path is the most reliable path problem. So in this case, we can transform it to a shortest path problem simply by converting every arc length to the negative log of the probability of the availability. So let's assume we have a graph where every arc represents a certain probability, and that is the probability that this arc is going to be available. So if the arc has a value of, say, 0.9, then that means we have 90% probability that the arc is going to be available when we want to cross it. And if the arc when the arc number is 0.2, we have 20% probability that the arc is going to be available. And we're trying to find the most reliable path to get from source to sink. Okay, so for the probability to make it all the way from the source to the sink, that is the product of all the individual arc probabilities. So we assume they are independent, they have nothing to do with each other. That means the product is justified due to independence of the arcs. And we seek the path with that maximum product. We want to maximize the product of these probabilities. But maximizing a product, that's equivalent to minimizing the negative of that product. right? Instead of maximizing the product of these p from I to j, we can use the minimum of the negative of that product. That's just very simple logic. You just flip the orientation and then you turn your maximization into a minimization. But that now is equivalent to minimizing the negative sum of the logs of the individual arc probabilities. So instead of minimizing the negative product, we can minimize the negative sum as long as we replace the arc probabilities Pij with the logarithm of these arc probabilities. Now we can use the sum. But minimizing the negative of a sum is the same as minimizing the sum of the negative values of that sum. The summons, they're called summons. So here we now have our problem in our typical shortest path formulation. We want the minimum of these arc lengths. There's also another rationale for this problem formulation. High probabilities would be around 1, so the log would also be around 0. Low probabilities would be around 0, so the logarithm would be a very largely negative, right? Because the logarithm of 0, if coming from the right, goes to minus infinity. So for a minimization problem, we want low numbers for desirable arcs and we want high numbers for undesirable arcs because we're minimizing, right? So we don't want high arc values, we want low arc values. So what we do, we simply take the negative log. As the log goes to minus infinity for x to 0 from above, we have a pole of the log at 0. Right? The log of 0 itself is undefined and we're coming from above, so it's going to minus infinity. So if we flip that sign, we have a largely positive numbers, which is exactly what we don't want in a minimization problem. So this function effectively is a penalty function because the closer we're getting to the pole, the more we're going towards infinity. So in a stepwise iterative procedure, we can get close to it, but we can never reach it because we're minimizing. So we don't want numbers that go towards infinity. On the other hand, high probabilities are desirable. High probabilities are 1, and the logarithm of 1 is 0, which is great for a minimization problem based on positive numbers. So this function effectively functions as a penalty function in the minimization. So high probabilities will be small positive numbers, with 100% becoming 0, which would be very preferable for minimization. Alternatively, you could use multiplication instead of addition in the Bellman equation, and we're going to use that in a moment. As mentioned above, it's usually better to think of it as the principle of optimality than as Bellman equation. And I've showed that here where I'm using the maximum, right? If we use the sum, that would be one particular manifestation of the Bellman equation. But here the principle of optimality causes us to use the maximum of two values. That is another manifestation of the principle of optimality. We have a different Bellman equation here. So back to the most reliable path problem. I think in general it's better to think of it as the principle of optimality and then develop your Bellman equation based on the actual problem. It can be understood in the strict sense as one particular equation. So as I mentioned, the Bellman equation is really just one particular manifestation of this principle of optimality. So now let's look at it. Let's take our example 2 and here it is again. Let's bring it back to memory. So we assume that the probability of every arc is at least 90%. I want to have some reasonable numbers. If I come with small numbers between 0 and 10%, then we don't really get a reliable arc. We want to make it possible. So I will assume that the arc availability probability is at least 90%. If we have a lot of arcs between 90% and 100%, given that we have the product for the overall availability, these numbers are getting pretty small pretty quick. So let's start with something that's at least 90%. Otherwise, the probability is too small. An arc availability probability is so small, like 50%. Do we even want to go there? I mean, we have to assume that an availability probability is fairly high, something like 90% or higher. For many cases, a probability of 90% is already unacceptable. So let's assume it's at least 90%. So then we'll simply take the inverses of the numbers of the problem above, and then I normalize this to the 90 to 100% interval. And then I take the negative logs. So let's do this data transformation here. I want at least 90% probability, and the rest I take the reciprocal, but I also divide by 10 because I want it to be scaled between 90% and 100%. And I think a plot may make this easier. So we see here, so we see that in our original data, the blue curve, we have a 1 at 1. So 1 is the lowest number that we can have in our network, and I want that to correspond to 100%. So 1 should be 1. And with the function transformation of the negative log, that's the orange curve, that's exactly where we get a 0 in the orange curve. So lowest number in the arc corresponds to 0 after the transformation. And we wanted our numbers to be between 90% and 100%. So that's the area between the green curve and the red curve. And you see that the blue curve is wedged in between those two numbers. And with that function transformation, that is the transformation from the blue curve to the orange curve, we obtain exactly that. Okay, so with these changes, let's look at our graph. I've blown it up to a big size so that we can read the new arc numbers. So we go from node 1 to 15, and you can see that we have these arc probabilities on the arcs after this transformation, and you can see that the three arcs that had a 1 are now 0, right? From 12 to 15 is a 0, and from 6 to 9 is a 0, and from 4 to 7 is a 0. So these are arcs that are maximum desirable because they have 100% of availability. So now let's use recursive fixing and reaching to solve this problem. Let's call it and look at it, and we can see that the overall arc availability is less than 20%. In recursive fixing, we have the value in the first node, so it's 0.1982, the 1982 here. And our path is 1, 4, 7, 9, 12, 15. And we can see that here we have a 100% probability arc in it, and also from 4 to 7. The other one, 3 to 5, is not included because the other arcs make it impossible. The other arcs that would be on the path would make it impossible. So that's our optimal solution that we have here. Let's do reaching, and let's look at that plot, and we can see that we get the same solution: 1, 4, 7, 9, 12, 15. So we get the very same path. Here now with reaching we have the optimal value in the sink, 0.1982. So we're getting different trees. And again, I'd like to point out that we have one branch here that is kind of completely useless, right? 1, 3, 5, 8, 11, but then there is no red arc from the 11 coming out from the 11 to the 15. So this gives us the highest probabilities from node 1 to 3, 4, 8, 11, but not to the sink. Again, that's not bad. Maybe we don't want to go all the way to city number 15. Maybe we only want to go to city number 8, and then we can read it off directly here in the shortest path tree. So a short comment, in my opinion, it's also a great example to show an entire long branch can be totally dead end. 1, 3, 5, 8, 11, what I just said, right? So it doesn't help to answer the question what's the most reliable path from source to sink, but if my interest is in all these nodes on that path, I have the answer. I have the optimal solution. I have the answer. Likewise, in recursive fixing, if we're interested, for example, from node 3 to the source node, we have that right here. It doesn't help if we start at node 1, but it does help if we start at node number 3, for example. That is the optimal path, starting at node 3. Okay, so next, note that we don't have to use the negative logs. We did that only to be able to use the shortest path functions, right? You will see that our minimization was using recursive fixing here and reaching, so we're doing shortest path. We did that because we had these functions already without further modification, and the Bellman equation in them is additive. So, but the Bellman equation are just a particular result of this principle of optimality, and it comes in different shapes and form. And in the following, we could use, for example, a multiply when we are designing f. Right? We want to be able to multiply f and t together and then use maximize instead of minimizing. This is actually the original problem because we wanted the product of the arc probabilities. We wanted to maximize the product of the arc availabilities. So if we take this project directly, we need to use a different Bellman equation. We need to have a different definition of f, and we can't use shortest path or longest path. But that's not a big problem. One thing to do, for example, is we have to initialize the starting node with 1, because if we start with 0, then 0 times anything is 0. We have to now start with the maximum probability, and that's 100%. Because when multiplying with 1, that is the 0. If you want 100% reliability to be the highest reliability, then our initial value must be 1. Otherwise, we are killing the availability right there. If we keep it at 0, then it would be 0 forever, because 0 times anything is always 0. If we do that a lot, it's still 0. So for maximum product, our initial value has to be 1. So okay, let's do that. We use the network again from the previous example, and here we still convert the arc lengths into probabilities, but we don't take the negative log because we're now changing it to a maximization problem. We don't want the log anymore. We now multiply these numbers together directly. So let's use recursive fixing, and we want to compute the longest path. Note that f of sync is now 1, it's not 0, and we multiply instead of adding in the Bellman equation. You see here that we are multiplying net times f, so that is t times f, and also when we're defining f, we need to take the maximum product, so it is t times f, and we are maximizing. Okay, so let's do it, and let's compute the solution here. And here we have different numbers because we are no longer using the negative logs, we're using the product. So the optimal solution from source to sink now has a probability of 0.82. It's not the 0.1982 anymore, it's now 0.82. But it is the same path. It is again 1, 4, 7, 9, 12, 15. Okay, and if we use reaching, it's the same thing, longest path with reaching. Here f of source is 1, not 0. So here we need f of source is 1. And we multiply instead of adding in the Bellman equation. So if we do this, then we're getting this solution. And the optimal path is again the same. It's 1, 4, 7, 9, 12. And we have the optimal product of 0.82 now in node 15. Okay, so again, recursive fixing and reaching show the same longest path solution, and the path matches the negative logs version that we used before with shortest path. In all 4 computations, shortest path with reaching and recursive fixing, as well as maximize the product with reaching and recursive fixing, we're getting 1, 4, 7, 9, 12, 15 as the optimal solution. Okay, So in the following example, we will see that a problem may seem daunting at first, but once you understand the project structure, it can sometimes be transformed or reduced to something that is much simpler. And in this case, we can use shortest path, which I bet you probably didn't expect when you hear the problem. So oftentimes in combinatorial optimization and math in general, the key is to have the right idea about modeling the problem correctly, and then to transform a given model or problem into another structure. And then you have the problem amenable to existing algorithms that do the work for us. And in this case, it's going to be shortest path. So you should try to find the hidden structures in a problem and then rewrite or transform that problem. And then you oftentimes can use standard algorithms. And it's not immediately clear that you can use standard algorithms or very efficient solutions such as DP when you first look at it. But when you really dig in and understand the structure, then simple solutions may become very apparent. You may or may not have to back transform the solution to the original problem when you're done. So the point I'm trying to make is an application of work smarter, not harder. Sometimes it's fairly easy to solve once you understand the hidden structure. So DP is oftentimes the most efficient way to solve shortest path or longest path problems. It's linear time. And this is in particular the case when the graph is sparse as opposed to being a complete graph. And a sparse graph, that is especially the case when you have a layered network. And this is an example of a stage in dynamic programming. A layered network represents a problem that can be solved in stages. So in the following, we won't be concerned with stages, but with a problem transformation into shortest path. So we have it in the following problem. So the rules are the following. We have 4 people who want to traverse a suspension bridge at night. And unfortunately, the bridge can carry at most 2 people. If it's going to be more than 4 people, then it's going to rip apart and everyone falls down and dies. So the 4 people have different ages, and therefore they need 5, 10, 20, and 25 minutes each in order to cross the bridge. And each party, and it should be clear this now has to be a party of 1 or 2, because at most we can carry 2. We probably want to exhaust that locally, so we probably want to carry 2, but 1 is feasible, 0 in theory 2, but that gives us no yield. So I think at this point it's 2. It's always going to have to be 1 or 2 people, and they must carry a torch while traversing the bridge at night. They cannot go without the torch, and the torch lasts no longer than 60 minutes. So can this problem be solved when we have these times for each person? 5 minutes, 10, 20, and 25. Those are the times that each of these people need in order to go across the bridge. So it turns out that this is really not all that hard to solve once we can analyze the problem and fully comprehend it, and basically what I call restructure it. So let's start at 0. A, B, C, D are still at the beginning. And when we have 2 people traversing the bridge together, then the time it takes is the time of the one who is slower. So that means the longer time. And starting with the first layer, what we show is always the people that are on the other side of the bridge. That means the people that have already crossed the bridge. So in the first column, that would be after C and D have traversed the bridge. The second, B and D have traversed the bridge. B and C have traversed the bridge. And the transit times are always the times for the party, and when it's 2 people, it is the larger time of the 2. So for example, when C and D cross the bridge, then C needs 20 minutes, D needs 25 minutes, so the arc is 25. When B and D go, it's 10 and 25, so it's 25 minutes. When we have A and C traversing the bridge, it's 5 minutes and 20 minutes, the larger is 20, so this arc is 20 minutes. So after C and D have crossed the bridge, so we now have C and D on the other side of the bridge. That means A and B are still on our side, on the beginning of the trip. So that also means C and D have the torch. A and B are in the darkness, C and D have the torch. And it now means one of them has to go back because A and B haven't traversed the bridge yet. So if D remains, and I said every node starting with the first layer now will always represent the people that have already crossed. So if D stays on the other side of the bridge, that means C has gone back. But when C goes back, then C needs 20 minutes. That's why we have C needs 20 minutes, that's here in the table. And to go from the state that CD is on the other side, and now we only have D and C traverses, that takes 20 minutes, because that's the time for C. If on the other hand C stays on the other side of the bridge, that means D has gone back, and D needs 25 minutes. So that's why this arc has a label of 25 minutes. And so forth, all right? Let's look at some at the bottom. A and B have crossed together, B stays, that means A goes back with the torch, that means 5 minutes because A's time is 5 minutes. If on the other hand A stays, then that means B goes back, that means 10 minutes, that's the time for B. Okay? So now, when D stays and C goes back, that means we now have a choice. We can have A and C crossing the bridge together, that would bring us ACD on the other side, or we can have B and C going together, that would give us BCD on the other hand, on the other side. Okay? If D is already there and BCD go together, then we need the larger of the times for B and C, and that's 20 minutes, and that's why this arc is 20 minutes. If D stays from the first passing, and that means C goes back, it means if now A and C go together, because D is already there, A and C going together, that's 5 and 20 minutes, so that's 20 minutes. So this arc is 20 minutes. All right. So in this case now, we always have 3 outgoing arcs. And in the next layer, as we go from the layer where we have 3 people on the other side, that means one is going back. That means we now have 2 people on the other side. Right? Before we had D, now we have CD. So we now have 2 people on the other side. But if we had BCD on the other side at the beginning, now we have CD. That means B has gone back with the torch, because A is still there. A still hasn't crossed the bridge. So he needs the torch. So one needs to go back. So if you want CD on the other side, that means B goes back. All right. So now B goes back. And when B goes back, that means C and D are remaining, and the time for B was 10 minutes, so that's why this arc is 10 minutes here. If, on the other hand, from BCD, B and D are remaining, that means C goes back, and the time for C is 20 minutes, this arc is 20 minutes. If from BCD, B and C are staying, that means D goes back, and D's time is 25 minutes, that's why this arc is 25. And so forth, right? So that means we now have the situation that we have 2 people on the other side, and we have 2 people having crossed yet, but the 2 people who haven't crossed yet have the torch. That's why one person had to go back. That's where we're going from 3 people to 2 people, because one is going back. So this one person now can partner with the one who just came back, and that means if C and D are already there, and we now want ABCD on the other side, then obviously A and B must be going together, and the time for A and B together is 10 minutes, so this arc is 10. If B and D are on the other side, coming from BCD, that means C has gone back. And to get from BD, C has come back, A was still waiting, we need the times for A and C. And for A it's 5, for C it's 20, together it's 20. That's why this arc is 20. Okay, so in the end, we have A, B, C, D together. To go from the first row to the second row, we always have one person going back. That's why an increase is always happening in 2, because 2 people are going together on the other side. And then we always have a decrease of 1 person, because it's always 1 person who has to go back with the torch. So it's from 0 to 2, then 1 down, so we only have 1 on the other side, plus 2 gives us 3, 1 goes back, that's why we have only 2 people here, and then the next step again, plus 2 people giving us 4 on the other side. Okay, and this is really, once we understand the structure, then we can solve it with shortest path. Note that the graph is relatively sparse, right? And if we had all of them together, connected together, we would have a full graph, and the number of nodes in that is n times n minus 1 over 2. So we get exponential running time. But we don't have arcs between all the nodes. In fact, we only have 4 intermediate layers, and all the arcs only go from one layer to the next. This really reduces the number of arcs that we have. Imagine from the first layer, we needed nodes to everything else. That would be an enormous explosion in runtime complexity, because we have so many arcs, and as we have seen earlier, shortest path is O of m, and m is the number of arcs. So that's why a layered network actually helps, because it can be done with adjacency lists, and that's the reason we can do it in O of m time. So let's model this net and let's plot it, and we see that it's getting a little bit more complicated, but we can clearly see the network structure in layers. It's a row of 6, then 4, then 4, and then 6. Okay, so with this data, let's do a shortest path. We use recursive fixing here, and let's do a graphics grid, and we see a shortest path tree on the left, and we see that one has a value of 60, so they can actually do it. You remember that the torch is out after 60 minutes. So we can actually do it in 60 minutes, provided we have it exactly as we have specified here and use the optimal solution for the people going back and forth. So we need to go nodes 1, 7, 10, 12, 16, 22. Let's also do it with reaching. And here as well, we have these layers 6, 4, 4, 6, and we are here getting a solution of 60 as well. Well, not a surprise, we knew that before. And the solution is 1, 7, 10, 12, 16, 22. So that means we have 1, 7, 10, 12, 16, 22. That means A and B go first, then A stays there, B goes back with the torch, then C and D go over the bridge, B waits. So now we have ACD at the destination. Next, A goes back with the torch, picks up B, and A and B walk over the bridge together. C and D are already there waiting for them. And this example is also another example that shows that the solution doesn't have to be unique, because another solution is AB, A, ACD, CD, ABCD. That means A and B go together first, B stays, A goes back with the torch. C and D go over the bridge together with the torch that A brought back. Next, B goes back with the torch, and next A and B go together over the bridge. Both solutions attain a value of 60. Well, that was pretty clear, right? If it's an optimal solution, then different paths have to attain the same value. The other solution, on the other hand, is 1, 7, 11, 13, 62. That is another solution, and we didn't find it. We didn't find it with our method. Both solutions, recursive fixing and reaching, gave us the same. 1, 7, 10, 12, 16, 22. 1, 7, 10, 12, 16, 22. Okay, so we have the case that not all solutions were found. Even though we used recursive fixing and reaching, both gave us the same solution. But here I propose is another solution, and we didn't find it. Okay, so to obtain that, there are a couple of methods to find that, and I will discuss them later in detail. I propose here a not so elegant solution just because it's quick and dirty and would still fit here. So the one I present here is not the one I would recommend, but it's quick and dirty and works. I present two other at the end of the session. So for this not so elegant solution, I have to cheat on the data a little bit, because in a tie, both recursive fixing and reaching may lean towards the same solution. When we have two solutions in F that attain the same value, then, well, which one do we want to take? Do I want to take 7 or do I want to take 7? Yeah, I want to take 7. So they produce two different solutions in example 3 above, but not here. So there's no guarantee to actually find it, right? Recursive fixing and reaching may find different solution, but they may find you the same solution, and that's the case here, right? We haven't seen yet that the 1, 7, 11, 13, 16, 22 is another solution. I still have to prove that. So let's do this by cheating a little bit on the data, because I want to show this proposed solution is valid as well. It's also 60. So we have that very often in combinatorial optimization. When you've found a solution, you only have found one of possibly many. You get one solution. The algorithm is guaranteed to give you an optimal solution. It's not guaranteed to be the only one. So as I claim that instead of 1, 7, 10, we can go 1, 7, 11, I want to delete the 7, 11 arc and replace its value of 10 with 9.99999. So for our practical purposes, that's still 10, but the difference is enough to cause the algorithm to switch. Right now it's not 7, it's 6.99999, and now we do have a difference. 6.999 is not the same as 7, so we do have a flip. So the path with the lower cost would now be 9.99999. Okay, so we take our net and we delete key 711, and instead of having it in there with the value of 10, we now put back a value of 9.999. Right? That's basically changing the value of an arc in that network. And then we call recursive fixing, and let's look at the solution. We have again the 60 in node 1 because it's recursive fixing, and then we have 1, 7, 11, 13, 16, 12, 22, right? So here we had 10 before, here was the 10. Now we use the 11. So that's a different solution, that's a different structure here. Let's also do it with reaching, and let's look at the plots, and we see that here we have as well 1, 7, 11, not 10. For the 7 goes to 11 because we faked the number from 10 to 9.999, and then 13, 16, 22 as we had before. So these two solutions are the only ones. There are only these two solutions, but we do have two solutions here, and the standard way only found one. Both recursive fixing and reaching found only one. The second one was brought to us by none of those two. So final comment on this one, in my opinion, also a great example that shows an entire long branch can be totally dead end. For example, 1, 5, 8, 14, and then 17, 19. 1, 5, 8, 14, and then 17 or 19. So here we don't really have any good interpretation for partial results somewhere in the middle of the shortest path graph. Here we're only really interested in, are they gonna make it in 60 minutes? So here we really need to know, can we go from the first node to the next node with 60 minutes? Here we really can have the interpretation that anything that is a branch that doesn't close up is indeed useless, as well as 1, 6, 9, 15, right? 1, 6, 9, 15, and then 18, 20, or 21. Completely useless because they don't close up to the 22. And here we cannot get stuck in the middle. Here we really need to close from source to sink. Okay, so next I want to solve the legendary knapsack problem with dynamic programming. The problem is pretty legendary. It has been around for decades, and it's also in many regards one of the simplest versions of dynamic programming and of shortest paths and of many combinatorial optimization problems that can be reduced to Knapsack. So we have the situation that a hiker must decide which goods to include in his knapsack. That's where the name comes from. It's a backpack for a hiker. And he must choose from among P objects. An object I has the weight Wi, and it has a utility Ui to the hiker. Right? Every item has a utility for the hiker, and it also has a certain cost. And that cost here can be size or it can be weight. Let's go with weight here because we want to have a weight restriction on the knapsack, not a volume restriction. It could be a volume restriction. It could also be done both, but then it's not standard knapsack anymore. And the objective is to maximize the utility of the hiker's trip subject to the weight restriction that he can carry no more than W weight units. So the knapsack has the following formulation as an integer program. So we want to maximize the sum of the utility values. We want to have the largest sum of these products of the utility value for item I times the binary decision whether or not we want to carry it. Xi has to be 0 or 1, so that makes it a decision problem. We want to make sure that we obey the weight restriction, but if we carry item I, then we get a utility Ui. So the sum of these items that we carry is what we want to maximize for the total utility of packing that knapsack. But we have to obey the weight restriction. So if we take item I and multiply it with its weight and we're adding all of these together, then it has to be less than the overall weight restriction W. We cannot carry more items than we can afford to carry in terms of weight. But if we can carry them, that would be great because we maximize the utility, but we have to obey the weight restriction. So, as I said before, usually here the key is to define the problem properly, and then we can use standard methods such as DP. So here we define our recursive function in a particular way, and once you understand it, then it's pretty easy. So we say dij is the maximum utility of the selected items if we restrict our selection to the items 1 through I and we impose a weight restriction of j. Okay, this is perhaps a little bit hard to grasp at this point, but we're going to see it visually in a moment. So that means our objective is to determine d of p and w, because we want to use as many items as we can. So we want to compute d of p. We want to carry as many as we can. That's why we maximize the utility values for up to item p. And we have to obey the weight restriction, right? That's why we are saying we want to have the maximum utility of the selected items, and we restrict our selection to the items 1 through I and impose the weight restriction. So clearly we have to use the items P in our DP, and we have to use the weight restriction. That's what we're gonna have later on as the stages. So we want to maximize P, and we are willing to exhaust our maximum weight restriction W for that. If we can meet this with an equality, that would be ideal. We want to carry as much as we can, but we may have to restrict it to being less than W, because we may have items that would get us over the weight restriction if we include them. So we determine this value d of p and w by computing d of ij for increasing values of I, because we want more and more items. So we have to use it for increasing values of I. And for a fixed value of I, this is important, that's where the name recursive fixing comes from. For a fixed value of I, we have to increase the values of j, that is the weight restriction. So note that we have two choices for every item 1 through I. It's a take it or leave it. Either you use the item or you don't use the item. If you do not use the item, then in these stages we have the same situation as we had before. So in that case we are using d of I minus 1 instead of d of I. Or we use the item, in which case we have to reduce from the available weight capacity by carrying item I. So in the first case, we have d of ij equals d of I minus 1j, because we don't take the item. So our d state has the same value as we had in the previous state of I, which was I minus 1, with the same weight capacity j still available. So you see here that it's the same j. We reduce I by 1 and j is unaffected because we don't take the item. So we are not using from unused capacity. So j is still the same. We need no further restriction here because we do not take the item. Relatively simple. Don't take it. So in the next state, it's the same as we had in the previous state in terms of p, and j is unchanged. But in the second case, we do want to take the item. So dij now is different. And we now get the utility ui for that item because we do carry it. So we do get the utility of it. And we progress from the previous stage, so that needs to be an I minus 1 here. But we also have to reduce the weight capacity. From j, we now have less capacity available. And given that we take item I, we have to subtract wi from it for that stage, because we do take them. But we do that only if wi is not larger than j. Because if it is, then we couldn't carry it. Right? So we have 6 pounds capacity, and after a while, after packing items, we only have 2 pounds capacity, and the next item that we want to carry is 3 pounds capacity. We couldn't take it. That's why it's very important that when we're talking about j, then we have to use a restriction that wi cannot be larger than j, because if it is, then we couldn't carry it. You can think of this equation as make some money, lose some capacity. So make some money is this ui. We're adding it. We're adding ui to d, and d was our utility value. So if we take item I, we're increasing utility by a number of ui. But at the same time, we lose capacity. Right? That's why we are adding ui, and inside the recursion, we are subtracting wi. Make some money, that's adding ui. Lose some capacity, that's why we're subtracting wi. Because then when we take item I, we add the utility of I and lose the corresponding capacity wi. Yeah, but this can only happen if wi itself is not greater than our remaining capacity j. Okay, this restriction is actually our capacity check. Without that, we wouldn't even check if we have enough capacity remaining. So here's an example. We have 4 items, 1, 2, 3, 4, and we have utility values of 40, 15, 20, and 10, and we have weights for these 4 items of 4 pounds, 2 pounds, 3 pounds, and 1 pound. So if we compute it with the recursion that we've just seen, we want the maximum of these two, right? d of I minus 1j, that was we don't take the item, or if j is larger than wi, then make some money, lose some capacity, right? And we want the maximum of these two. So the maximum of this d expression and of this d expression, but restricted to j larger than equal wi. Okay? And if that weight restriction is not met, then it's 0, because we can't take the item. So we're adding a 0, right? We lose a step. We have I minus 1 here, but we're adding 0 to it. So that means we have to skip the item. We go to the next one. And we want to compute, where did I have it? Here, d of pw. So we're computing d of 4, 6. In this example, we're going to have a weight restriction of 6 pounds. And we have maximum 4 items. P is 4, right? P was the number of items that we have here in the sum, I from I to p. So we want d of pw. So we have 4 items and we have a total weight restriction of 6. So let's run it and let's display it as a table, and this is the resulting table. Now I think I have to explain this field by field, so please bear with me. If you know this already, you can probably skip something like 5 minutes, but I think I need to explain this result. So first note that we start these values at 0. I is 0 and j is 0. And that means if we don't carry any items, we have no weight consumption, but we also have no utility. That's why the first row and the first column are 0, right? It's like not packing anything in the backpack. I might as well leave the knapsack at home, go without it, right? That's the best thing. If I get no utility out of my knapsack, then why even have it? So if you don't carry anything, it has to be zeros. But now we progress item by item, and for a fixed item, we go higher with the weight restriction. And remember that this is step by step. So we are only including the first item in the first row. We only look at item 1 and nothing else. And the columns now represent the weight restrictions. So if we take only item 1 up to item 1, that means no item or item 1, then for 1 pound weight restriction, we can't carry it because its weight is 4. So that's not going to work. Now we give a 2 pound weight restriction. Is that going to work with 4? No. Not with 3, but with 4 pound weight restriction, it's going to work. So we can now put item 1 in our knapsack because it's less than or equal of 4, and that gives us 40 units of utility. Again, right, this is utility. We're looking at D, and D is the utility that we're going to get. So we maximize utility. We're trying to cramp in as many items P that we can. We have to obey the weight restriction. But ultimately, this is a table of the utility values which we have in D. Okay, so I think this row should be clear for 0 items or 1 item. Now let's look at the third row. This means we allow 0 items, 1 item, or 2 items. And again, we start left to right with the weight restrictions. So if we give it 1 pound, what can we carry? Well, nothing. We are restricted to items 1 and 2 at this point. We can carry something with item 4 that has a weight restriction of 4, but we're not there yet. We're going to do our 4 in the last row. We are still restricted to items none, 1 and 2. And with 1 pound, we cannot carry it because 1 needs 4 pounds, 2 needs 2 pounds. So we cannot really do anything with We cannot do anything with 1 pound, but when we have 2 pounds weight restriction, then we can include item number 2 because it has a weight of 2, and we do allow up to 2. So what can we put in? 15. So we have 15 utility values here. We cannot put in 4. We cannot put in item 1 because that would need 4, and we still have a weight restriction of 2 at this point. So now let's raise it to 3 pounds. What can I put into my knapsack when I have up to 3 pounds available and I'm restricted to items 1 and 2? Well, nothing changed. It's still only item 2 because 2 is less than 3 pounds. The 4 would be more than 3 pounds, so I still can't take item 1, but I can easily take item 2. So this is the same as before. So we are at 15 values of utility. Now we give it 4 pounds. What can I put into my knapsack when I have a weight restriction of 4 and I'm restricted to items none, 1 and 2? Well, now I can suddenly put item 1 back into my knapsack because I allow up to 4 pounds. I could also put item 2 in it, but that only gives me 15 utilities in that values. And we are maximizing, so the larger one would be item 1 because that gives me 40 points. So here, when we have 4 pounds, it's better to take item 1 and not item 2 because I get more utility value out of it. Let's go to 5 pounds. If I can do 5 pounds, what can I do? Still restricted to none, item 1 or item 2. Well, with 5 pounds, it's the same situation as before. I could put in item 1 or item 2. I cannot put in both because that would require 6 pounds. So what do? Well, I take item 1. Item 2 doesn't fit. So here we still have the 40 pounds. But now I'm coming to the point that I allow 6 pounds weight restriction. What can I pack when I have items none, 1 or 2? Well, I can put both of them. It's 4 plus 2, that's 6. That's not larger than 6. What utilities do I get? 40 plus 15, that gives me 55 points. All right, so next row, I'm now gonna allow up to item 3. So for this row here, we're looking at no item, item 1, item 2, or item 3. Let's do the same thing. So if I give it £1, I can't do anything. I can't include item 4 yet. I'm only 1, 2, 3 or nothing. So with £1, I can't do anything. 4 is larger, 2 is larger, 3 is larger. If I allow £2, well then as before, we can take item 2. If I allow £3, well, here it's now getting interesting. I could put the 2 in easily. It would be less than 3. But I can now put in an item that exhausts those 3 but gives me more utility value. 20 is more than 15. So I would now prefer item 3 and I can put it in because I allow up to £3 and item 3 takes £3. So I put in item 3 because it gives me 20. All right, that's why I have a 20 here. £4. If I now allow up to £4, well, I could take item 2 again, but that only gives me 15. I could take item 3, but that gives me only 20. When I can exhaust £4, I can get 40 utility value numbers if I use item 1. So here I get 40. The same in the next one, up to £5, it's the same situation. I can put my £4 into it. I could also put items 2 and 3 into them because I have £5 and their weight is 2 plus 3, that's 5. So they would fit in, but 15 plus 20 is only 35. That's not enough. I can get more utility value with item 1. The 40 is larger than the sum of these two. And I save £1. So last one, up to £6. Now again, it's better to use items 1 and 2. With £6 again, I could take 2 and 3, but that only gives me 15. But that only gives me 35. I'm better off going with item 1. And in the last one with 6, I can now put £4 plus £2 with £6, and that gives me 40 plus 15 is now 55 as we had before. So now in the last row, we include all the items 1, 2, 3, 4 or nothing. Okay, and a similar argument now gives us this row. So if I allow up to £1, suddenly item 4 is interesting because if I can put only £1 of weight into my knapsack and I can consider all 4 items, the only one that fits is item 4 because it's the only one that only consumes £1 and it gives me utility of 10. So here we have a 10. 2, it's the 15 that we had before. And now it's getting interesting for weight restriction of £3. In items 1, 2, 3, we had 20 utility values. That was because the item 3 was exhausting it with £3. But with 4, we now have a different solution. We can get 25. And that comes from the fact that I can create £3 of weight, not just by using item 3, but I can now also use items 2 and 4 because item 2 has weight of 2, item 4 has weight of 1. Together that's 3, and that gives me more. It gives me 15 plus 10, that's 25. That's more than item 3. So here suddenly, just by allowing the 4th item included in the consideration, I have 25 utility values, and that is no longer item 3 that we had before when we didn't look at item 4 yet. It is now 25 utility points because 2 and 4 together give us more utility than item 3 alone. Okay, if you now have 4 points, then again we are back to what we had before. It's item 1. The 40 is just pretty strong. The 40 here just wins over all the other combinations. For a weight restriction of 4, that is, right? If we go to 5 and 6, it changes now. With 5 pound weight restriction, we can do items 2 and 3 together. That would give us 15 plus 20. But 15 plus 20 is only 35. We're better off using the 5 pounds with items 1 and 4. That gives us 4 plus 1 on the weight and 40 plus 10 on the utility. So that's better, so we get a 50. And then back to 6 pounds. And again, that makes it unbeatable taking items 1 and 2, because we have 6 pounds in weight and 40 plus 15 utility. Okay, so you see that this is the correct recursion, and we see that numbers change and flip inside the table. So by doing this in states, first state is by item number, and then for every row going by weight restriction, one at a time, gives us an optimal solution. We now have the entire table. We could look this at various ways, but what we really wanted was really maximizing the utility of the backpack, and that was simply D4 and 6. So this D4 and 6 is the same as we have here in the 55. And this is the maximum that we can get with those 6 pounds weight restriction. Okay, sorry that took a bit longer, but I think I needed to explain this table. And now that we have it, let's use a much larger example. How about we have something that has 80 items and we have a weight capacity of 40. So if you think that's crazy for a backpack, then think something like a space shuttle where 80 items of cargo need to be carried, and we have a weight restriction of, well, 40 weight units. So probably be more than 40 pounds, probably won't be 40 tons, whatever, right? Take a weight unit of this for these numbers. And if we now compute this, then our optimal value D of size and capacity is 407. And we can look at the whole table, even though it's a waste of effort. We get the 407 in the lower right corner. We have this down here. You see the 407 down here, right? But it's a complete waste. We don't need the whole table. We just needed D of P and W. So with this, now let's look at a much larger problem. Now we just can't print this tableau anymore, but we also don't need it. So let's say we have 1,000 items to look at, and we have a weight capacity of 500 pounds or tons or whatever. This could, well, perhaps an ocean tanker could have numbers of these dimensions. And again, we are only interested in D of the size and the capacity. And you see that we can compute this still rather fast, okay? And plenty of random numbers between 1 and size for our utility numbers and our weight numbers. Okay, at these large numbers, I just needed to use random numbers. So we emphasize that for this computation of the solution, we don't need the whole tableau. It's totally unnecessary. We're just interested in this number, D of size and capacity. And in fact, many of these Dij in the tableau are never computed. And with this, I'm making the point that sometimes instructors say that you need to construct the tableau and then you need to find your number in the tableau. No, you just need to compute D of P, W. You don't need the whole tableau. Many of these items in the tableau would be never needed. And to show this, I modify my recursive definition for D a bit. Before the return of the max, we store a 1 in another array E, which was previously initialized to 0, and then I want to look at all the values of E. So let's do the same thing again. I now use 150 items with a capacity of 75, just to keep it manageable and display a table that I can show on the screen. So we get 1450, but what I now want to show is actually the table E. I have initialized it to be 0, and before I return the max in the recursion, I just want to store a number of 1 in it. And if I now display it, then you can see that we have plenty of zeros, especially more towards the bottom, right? You see that here when we go to the bottom, we have plenty of zeros in them. The 1 means we have computed it in the tableau, and we would have needed it anyway in order to compute D of P, W. 0 means we now have it in the tableau, but we never needed it if we just want to compute D of P, W. So doing the whole tableau is a waste, especially further down in the rows of the tableau. We're guaranteed a 1 in the lower right corner, and with the tableau we compute way too many numbers that are never needed if we do it without the tableau. So we can also quantify this. So let's compute this here. So if you do the tableau, then here in 21% of all the computed numbers, you've done it in vain. You didn't need it, right? You still needed 80% of these numbers in the tableau, but these 21% are completely wasted computation effort. You didn't need it. So we can see that the tableau is really only useful for educational or debugging purposes. If you want to apply DP for Knapsack problem, and I'm not saying this is necessarily the most efficient way to solve Knapsack, there are more efficient ways to compute that, but my point is here not to explain Knapsack, but use it as an example for DP. It is, however, the most code efficient way that I'm aware of. And then DP shown above really is just one line of code. It's one recursive equation, one formula, right? Look at how code efficient this was. This is our recursion line. You can't really get this much shorter. And you need an initialization. I memorize, so I have to use clear D. More on memorization later. Then I initialize it, use the recursion, and that's really it. The rest here is just data. So I find this incredibly efficient. It's the most code efficient way, but definitely DP is not computationally the most efficient way to solve Knapsack. And then you have to keep in mind, we won't compute the whole tableau, but we simply compute D of P and W. Then it computes only the minimal amount of numbers. Actually, I want to highlight this. That it needs. Another application of optimization. You should be parsimonious with the amount of data and computation you need. And again, this is a manifestation of the principle work smarter, not harder, or my eternal principle, don't handle or compute data you don't need. So I want to give a closing comment on Knapsack with DP. Usually when Knapsack with DP is taught, it's done as a longest path problem in a network. So I'll show you that here. And personally, I find that way more complicated than using the simplicity of the recursive method I've shown you above. If you do it like this, and here you see it with just 4 layers, then you have to set up all the nodes and arcs, and you may have to do this manually. And for larger problems, this is very tedious, as every item represents a row, and every weight, which is also a cost unit, represents a column. So for our problem above, this would be the network representation. We have 40 to begin with, and then you see in layer 1, we have always 0 going to the right if we don't take it. We always go diagonal with a 15. That was the restriction for item number 2. For item number 3, it was 20. So again, to the right is 0 for every arc here, and going diagonal is always 20. And you then need 10 for the last item. So that's a lot of nodes that you have to set up. That's a lot of arcs that you need to set up. Then you will get the shortest path here will be S, the source, and then 1, 4, 2, 6, 3, 6, 4, 6. So it's this path here from here going down to 1, 4. That is 40. Then you go to 6. That's here. You add the 15. That's the 55. And now you add 0, 0, 0, that gives us the 55 that we had previously computed. So this is the optimal path in the network representation. So you do a lot of setup work, and I think it's simply not warranted. So conclusion on this, the longest path approach to solve Knapsack is not very efficient for the practitioner. And I've left out a few items up here. You have to ensure that you either manually set things up with a topological ordering, and you have to write code to create a topological ordering. And now you need a longest path algorithm on top of it. So first you create a network, and then you need a shortest path algorithm on top of it anyway, right? So you could use a simple DP version shown above, or use a dedicated longest or shortest path algorithm, Dijkstra, and there's several variants of it. But now we are back to DP, right? Because they're all manifestations of dynamic programming. Dijkstra is basically dynamic programming in disguise, and Floyd Warshall is dynamic programming in disguise. because all these algorithms have DP at the very core. So if you use DP anyway, why create the network before? So I think these 3 points together pretty much sum it up, and I conclude that the longest path approach to solve Knapsack is not efficient for the practitioner. And the DP that I've shown above also is not the most efficient, but I think it's not the most efficient in terms of running time, but I think it is more efficient in terms of work to configure the problem. All right, so in the following I will show you a particular type of DP problems that we haven't looked at before, a very important type that has the costs modeled in nodes and not in arcs as we've seen before. So I suggest you don't fixate on modeling the transition costs in arcs. Oftentimes they are given as or can better be modeled with costs in nodes. So in these cases it would be possible to rewrite the problem with arc costs, but that would be very, very tedious. And Knapsack above was already an example of a problem in which solving it directly with DP is much more efficient than trying to build a graph that uses arcs that represent the costs just to be able to use shortest path or longest path. So the Knapsack graph shown above is a lot of work and only for 4 items, right? See how many nodes we needed, so see how many arcs we needed. And in contrast, the following example shows you DP can shine in spades with its breathtaking code efficiency without any arcs and graphs altogether. And if you're not interested in the solution but only in the value of the solution, then it's even shorter. So oftentimes we have the costs as table entries in a matrix. So here we don't have any transitions. Here the costs are in the nodes themselves. And for this particular problem, the rules are as follows. You start at the top left, so this would be this 0 up here in position 1, 1, and you have to get to the bottom right. That would be this 0 down here in position 4, 5. And you can only move to the right and down. You cannot move left or up, right? So if we take the 6 here, the only way to progress is to go to the 8 here, 1 to the right, or down. This would be this one here. You cannot move to the left, it would be this 8, or going up, that would be this 3. Right? So you can only go to the right or down. And we are looking for the cheapest path to get from the position 1, 1 to 4, 5, or the other way around. So obviously we're going to do both. So here we have costs in nodes. Here they are in table entries. We don't have any costs as transitions between nodes. We have them in the nodes themselves. So with this piece of code, we're going backwards from 4.5 to 1.1. This is similar to recursive fixing. That means we have to initialize the topmost row and the leftmost column with infinity, because we don't want to take them and we're minimizing, so we can never really take infinity because we have a minimalization problem. We have to initialize 1, 1 with 0, because that's where our recursion ends, right? We start here in the lower right, we want to end here in the top left. So at 1, 1, it has to terminate with 0 costs. And then the recursion is really fairly simple. We are looking at the lower of these two numbers, the left neighbor, that is I, j minus 1, or the neighbor above, that is I minus 1, j. The lower of these two numbers is what we're gonna take. It's the minimum of T1 and T2. I've intercepted T1 and T2 here. That makes it easier to append them to the path. So what we need here is the minimum of di, j minus 1 plus mij and di minus 1j plus m of ij. But if we look at this closer, then this is really just the minimum of these two d terms plus the matrix entry. Right? It makes it a little bit simpler, and that's what I have here. It's minimum of T1, T2 plus the matrix entry. Okay, And when we do this, we now have to compute d4, 5. We have to compute that the recursion value of 4, 5, and the recursion ends when we have d1, 1. Okay, so let's compute it, and we get a minimum value of 24. So if we want the actual solution, then we have to extract the nodes, we have to extract the fields from path. That's why I have appended to path here in the recursion. And this is probably a good idea to bring in nest and nest list. So it works as the following. When we have path, we initialize with 4, 5. Nest list is a function that applies a particular expression to an initial expression again and again and again. And the output is always fed in as input again. So we initialize with a certain value, with a certain expression, here 4, 5, and we do it 7 times. That's because we have 7 elements in the path from 1, 1 to 4, 5. And then what we need to do is that we are interested in the predecessor, because we're going from lower right to upper left. And we do that with the cases where the values that are being fed in from a computed results are in the right position, and we're interested in the left position because that's the predecessor. But the predecessor of one particular node here is the successor in the previous step. So the output we'll feed back in as the input in the next stage. That's why we use hash here. So let's look at this closer. Let's first run it. So this is our nodes 1, 1, 2, 1, 3, 1. This is the way we go from 1, 1 to 4, 5 for a value of 24. So let's look at this a little bit closer, how nest list works together with these cases. So we take cases and we initialize with 4, 5, and we see that we have exactly one predecessor of 4, 4. Right? Next, we see cases always returns a list, but we only have really one element in here. That's the transition from 4, 4 to 4, 5. So we want the first of it, because we really want this one element from the list. And now, what we now want is the predecessor. We started with 4, 5, but that's the end, right? That's the successor. To get the predecessor, we take the first list element. So we take another first of this, and we get the 4, 4. Now, given that this is nest list, this is now the output from this expression here that's inside the nest list. And this now becomes the input for the next stage. But if we're looking at the previous transition, what we just computed is the successor of the previous stage. So therefore, the hash really has to be in the second position here, right? It's like taking this 4, 4, making that the successor and looking at the predecessor, and that's now 3, 4, right? So we go from 3, 4 to 4, 4, and from 4, 4 to 4, 5. Here is the 3, 4. So now if we iterate this, then we're going all the way back to the 1, right? And that's why we're getting this solution. So I highly recommend you get familiar with nest list as well as fold and fold list. They're sometimes described as a functional way to perform recursion. And that's really what they are, because the output is immediately fed in as the input for the next stage. And this way we are computing the entire path backwards from 4, 5 as starting point all the way to 1, 1. All right, so with that we have computed our solution, and in the next step let's go from 1, 1 to 4, 5. So now we have to initialize the 5th row and the 6th column as infinity. Again, we are minimizing, so in order to make sure we're not getting out of bounds, we make them infinity, because in a minimizer infinity is never taken. We now have to initialize d4, 5 with 0. Up here it was 1, 1 to terminate the recursion. Here we need to terminate the recursion at 4, 5. And now we need to compute d1, 1. Right? You see, we terminate at 4, 5 means we need to compute d1, 1. Here it was the other way around. We terminate the recursion with D11, so we have to compute D45 here. So let's compute it the other way around. We also get 24 as the minimum value. Let's compute the path again with nest list, and our solution 2 now is this path from 1, 1 to 4, 5. Question now is, are they identical? Yes, they are. So we get this as the one and only solution with a total value of 24. Okay, if you're not interested in the solution but only in the value of the solution, then the recursion is even simpler. We don't need to intercept the step in a path that we are appending to the path. We just basically take this minimization that I've explained above, the minimization of these two D terms plus the value in the matrix. So this is even shorter than what we had above, and we get 24. And from 1, 1 to 4, 5, similar thing, we get 24, right? So again, I think this is super code efficient, and we get a minimum path through a table, right? For real life problem, you would make it a bigger table, but the algorithms don't change. You would just change the initialization values and then the number that you would compute. So you could do this with a 30 by 30 table, or 100 by 100, or 1000 by 1000. You would initialize with 1, 1 and then compute D for the lower rate value, right? If it works for this small 4 by 5 matrix, it's gonna work for 1000 by 1000 or whatever. Okay, so I think it would be awkward if after a lowest cost path problem I wouldn't use the same data for a maximal cost path problem. So now instead use the maximization here. So again, we go from 4 to 5 to 1, 1 in the first path. We do the initializations similar to what we had above, except now we have to have the upper row and the leftmost column as minus infinity, right? When we are maximizing, then we have to make sure we don't go out of bounds by using minus infinity, because a maximizer would never take minus infinity. Again, we initialize D11 as 0 and compute D4, 5, and we get a maximum path of 44. So again, let's compute a solution. Here is the solution. Let's go in the opposite direction. Let's go from 1, 1 to 4, 5. Again, we now have to initialize the bottom row and the rightmost column with minus infinity. Initialize D4, 5 with 0, compute D1, 1, and we get 44 again. Now let's compute the solution and ask the important question, are they identical? And here we have the interesting case that our two solutions computed forwards and backwards are not the same, right? Their solution values are, but the solutions are not. So let's look at them, and we can see that we have these two different solutions here, but they have the same value. In this cell here, that is 2, 4, in one case we go to the right and down in order to get 887, and in this case we're going down and then to the right also to get 887. It's the same thing, we're getting 887, but given that we have an 8 to the right of this cell and also down of this cell, then we have these two possible solutions, different paths, same solution value. And here as well, if you're not interested in the solution but only in the value of the solution, the recursion is even simpler, right? From 4, 5 to 1, 1, this shortcode, from 1, 1 to 4, 5, this shortcode, 44, and we really are just performing this maximization of these two D expressions, basically the neighbor to the right and the neighbor down, plus the cost that we just look up in the matrix. Okay. So in the next example, I want to demonstrate that we're now completely leaving this shortest path world. And the more we do this, the more we leave shortest path, the more it becomes necessary to spend more time on focusing on state and ensuring that we configure our problem solutions correctly. With shortest path, it was relatively straightforward. Every node was a state. But outside of a shortest path context, things get a little bit trickier. So first, let's make things a bit easier with the terminology, because it can be confusing with state versus stage. Some authors make a distinction in terminology between a two-dimensional state, for example n, q, and instead call n a stage and q a state. And if your author does that, then be careful to understand exactly what stage and state are. And you may find it useful to call the two-dimensional point n, q the state itself. And I happen to be in that camp. I find it easier to have a two-dimensional state than to have stages and states in the same modeling problem. And in general, this can be an n-dimensional state, not just a two-dimensional state n, q. And below, I'll visit up to a three-dimensional state. I'm not going to go beyond 3 dimensions. And I think what further confuses the matter is the fact that in the early literature about DP, the authors used the word stage for what we now call state. So if you look at publications from Bellman and Nemhauser, you will see that they're talking about the multi-stage optimization. And at the beginning, we've seen that it was called multi-stage optimization by Bellman himself. And I think this is rather confusing. Today we are using the word state for that. And I refer you to the quote from Bellman at the very beginning. That's where he is always using the term multi-stage optimization, where every stage had to be solved one at a time, which was the reason for the word dynamic. Okay, so dynamic programming is massively more powerful than the restrictions to shortest path may make one believe. And to harness the full potential, it becomes crucially necessary to clearly define what state is and to define state properly, along with the border or initial or terminal conditions. Recursion inherently depends on proper initialization. You will remember this from your undergrad class where you had induction. Just one initialization wrong, and that can be an index or an index range or an initial value, and the whole DP recursion is totally thwarted. So here a good understanding of induction really helps. You should ask yourself just what is the induction anchor and what is the induction inheritance. If you do just one of them wrong, then the whole recursion induction DP program recurses into nirvana and you're computing either the wrong thing, you may even crash your computer, get an infinite loop, whatever. Many things can go wrong here. And I think in a way, induction, recursion, and DP describe an evolutionary process, similar to what initial value problems do in differential equations. So you make a mistake in the initial values or the differential equation, and the evolutionary process is no longer what you wanted to model. So no algorithm knows what you want, it can only do what you tell it to do. So it's very important to set this up correctly. So, but if you configure the problem properly, and I know that can be complicated, but then DP will absolutely dazzle you with its mind-numbing code efficiency. In general, recursion is quite frequently the most code efficient way to program. And in a few programming languages, this is given extra emphasis. In Scala, for example, you're generally recommended to program recursively unless you have superior reasons not to. So think clearly what a state is. So this is kind of a definition of a state. A state must be a summary of what went before that is sufficiently detailed to allow the evaluation of current alternatives. Right? It's a bit of a summary. It captures everything that was done in multiple stages before and now captures certain optimal value in one stage, and we're now going to the next stage. And I point out that before in this context can also mean after, as we iterate forwards and backwards through the states of a DP problem. So states are the points at which decisions are made. They are decision points. That's what we call a state. And the set of states is called the state space. And I point out that this is very similar to what we have with the states in Markov models. In Markov chains, also transition occurs via independent states. So there's a very close link between the states in dynamic programming and the Markov chains. All right. So in the following example, we want to find the length of the maximum length substring palindrome of a given word. So, for example, a single letter would be a valid palindrome because it can be read forwards and backwards. And we do not require the palindrome to be contiguous in the string that we start with. So the letters can be anywhere in the string, can be contiguous or non-contiguous. So from this, the following points should be fairly straightforward and immediately clear from it. If the length of the substring is 1, we have a valid palindromic substring. The length is 1. Well, take a letter. A letter is a palindrome. And a consequence of this definition of a palindrome is that the leftmost and rightmost letter has to be the same. Otherwise, you can't have a palindrome. So when the letter for the index from the left and the letter for the index from the right are the same, we have a valid palindromic substring. And this is the condition in the outermost if that we have here. And the outermost if, that's the condition here. That's the condition in the outermost if. And if it's true, then we have to recurse. We have to go deeper and find more because we're interested in the maximum substring. Otherwise, we take the max of the two solutions we get by incrementing the left index and decrementing the right index. And if the two indices are the same, we have the case above. It's one letter and we're done. But if the two indices are different by only one, that means the two letters are contiguous. We have a two-letter palindromic substring with nothing in between and we're done. So this is here where we have I plus 1 equaling j. Right? I mean, we could take this an equation and subtract I from both sides. Then we have j minus I is 1. So the letters at positions I and j really are next to each other. They're contiguous. And in that case, we cannot get between them. So we have a palindromic substring length of 2. But if these two letters are the same and they're not contiguous, then we have 2, that's for the two letters, plus whatever is in between, and we now go inside there by incrementing the left index by 1 and decrementing the right index by 1. Right? So if they're contiguous, it's 2. Well, it's the two letters that are next to each other. Otherwise, it's 2 for the letters plus whatever we can find in between. And if that's not the case, when the letter for the left index and the letter for the right index are not the same, then we have to go also into that recursion and we have to increment the indices. We have to increment the left index by 1, leave the right index the same, and the other recursion that we need to submit is for the left index the same and the right index decreased by 1. And we are looking for the maximum of these two. It can be this one or it can be this one. We're looking for the maximum because we're looking for the maximum palindromic substring. Okay? The two indices are not the same and not just one apart. We have at least a 2-letter palindromic substring, but still have something in between, so we're not done yet. Next, increase the left index by 1, decrease right index by 1. Okay, so we are at least guaranteed a 2-letter palindromic substring. So here's an example. If we have u and a bunch of stuff in between and we're ending with u, will give us at least uu, but maybe we get more. It depends on whether or not these two letters are contiguous. Okay, so let's evaluate this, then let's run it on a couple of words, and we can see that we really are finding the maximum substring and we are including single letters as palindromes. So if we're looking for the maximum palindromic substring of u, it has a length of 1. Well, that's just the letter, and the letter is a valid palindrome. If we look at uu, we get 2, right? That it's a palindrome and they're next to each other. If we have ueu, that's a palindrome of length 3. If we're adding one letter at the end, that doesn't change anything. The D has nothing to do with the palindrome, so we now have a length of 3 again. If we take a word that has all letters different, well then the maximum palindromic substring is obviously having a length of 1. You can take any letter of this. There's no palindrome inside there except for every letter itself. So here are some longer words. Here we have underqualified, and it has a length of 7. And if you look closer, if you do this by hand, you're gonna find out it's the word deified. It's deified, right? That's the word that we have inside there. And we also have rotor. That's a palindrome in itself. We get a length of 5. If we take rotator, we get 7, and that's because rotator itself is a palindrome, but it contains rotor inside. But we're looking for the maximum palindromic substring. So even though rotator contains rotor, it's not the maximum palindromic substring. It would be rotator with 7. And if you look at the crazy word turboventilator, then you will find that the maximum palindromic substring here is actually rotator. Okay? So next I point out we could make it even shorter by leaving out the memorization. And that way we also don't need to clear out the function definition every time. We have to do it one time now because we have memorized on L. But if we don't use memorization, we also don't have to clear out the function definition all the time. But then we lose speed, which for short examples such as English language words would never be a problem. But we can have large strings like DNA sequences, for example, and now without memorization this would be exponentially inefficient. But for English words, even long English words, it doesn't matter. And you can see that we're getting the very same results here as we had above. Okay, this is without memorization. Recommended for short strings, not recommended for long strings. All right, the next problem, I want to show you that even though a problem may sound daunting at the beginning, if you have a proper understanding of the states and then correctly model your recursion, it's extremely code efficient and fast to solve. So this example is called trout poaching, and I think you will agree with me, once you fully understand it, and that is a bit tricky to understand, I think, then it's an incredibly simple recursion. So we have a trout poacher who is planning to poach in the national preserve, and the preserve contains K lakes. And as a careful planner, our poacher has assembled the following data. Y of I is the number of trout he expects to catch in 1 hour's time at Lake I. It's important, it's 1 hour time restriction, and we are at Lake I. And T of I, j is the travel time as a non-negative integer in hours from Lake I to Lake J. So to go from one lake to another, he needs to travel, and the time for that is T of I, j. And the poacher figures that there is some risk of getting caught by the game warden. And to minimize that risk, he has decided he will fish for only 1 hour at each lake that he visits. 1 hour, that's it. And then he needs to leave because there is the risk that the game warden may come. But he allows himself the option to return to a lake he has visited before after he has been to another lake, as he figures the game warden will most likely have left by then. And he's away from any lake for a substantial amount of time because he will have to spend at least 1 hour at another lake, and it may be multiple lakes, and there will be travel times, right? He needs to go from Lake I to Lake J, and at the very least that's the time that he has. From I to J and then back to I would be time from I to J plus 1 hour plus time from J to I. But there may be multiple lakes that he visits, not just one, and they have even more travel time, so the total time is quite a while. And we assume that he just arrived at Lake 1 and now it's 12 hours until dinner. So we now have to think really hard what constitutes state. So we have to think about this problem a bit more detailed. There's two things to keep in mind with this. It may be optimal to leave Lake 1 immediately. Just because he arrived there doesn't mean he has to start fishing there. It may be more profitable for him to skip Lake 1 and start fishing in the other lakes. That depends on the expectation y of I of what he can catch at another lake. And it may also be optimal to fish for fewer than 12 hours because he has travel time and he needs to get back. So in this case, we will set up the pair n, I as a state, and that means leaving Lake I with n hours of time remaining until dinner. And we could also configure this DP differently. We could also model it as arriving at Lake I with only a few modifications, but I think it's easier to understand it this way. We now define f of n, I as the largest number of fish he can catch in n hours, given that he is leaving Lake I. It's important here to understand our decision point is when he is ready to leave a lake, not when he arrives there. Ready to leave a lake, that's the decision point, because now he needs to figure out what lake am I gonna go next. And we include in f of n, I the yi fish he just caught at Lake I, right? So with that component, with y of I, he's looking backwards. How many fish did I just catch? But my decision point is when I'm ready to leave, because now t of I, j comes into play, right? So it has a component in it that looks back, what did I catch? And it has a time component that looks forward from that point, right? So what we're looking back is utility, what we're looking forward is the time restrictions. So then comes his decision is where do we fish next? If he chooses Lake J, he leaves there t plus t of I, j plus 1 hour later, right? Because he needs to get there and then he needs to fish there for 1 hour. So it's t I, j plus 1 hour. He needs to get there and then is there for 1 hour. And this gives us the following functional equation. And this one I think I need to explain a bit more in detail. So when he's ready to leave lake number I, what he just caught is yi. That's what he just caught in terms of utility. And we are maximizing the utility, we are maximizing the fish estimation that we can get there, which is why yi is outside of the recursion. It's outside of the max that we are using inside the recursion. Right? You remember this from before. The utility is always added to the maximum or minimum. Utility is probably always added to a maximum. And then the time restriction goes inside the max. So in the left argument of n, that's the time restriction. When we go to the next one, we have to subtract tij plus 1 hour from n, because that's the time that it takes. We need to get there and then we need to fish there for 1 hour. So from n, we are subtracting tij plus 1. And we leave for lake number j. And j needs to go over all the lakes except for I, because that's the one we're leaving and we wanted to leave after 1 hour. So we're finding the maximum of these f values for all lakes j that are not I, because that's the letter we just finished. So this is when we still have time remaining. This is for n larger than 0. And we need to terminate the recursion as well. We don't want a negative infinity value and then get a recursion that never terminates. So if n is negative, we have to stop. That's why we here are saying 0. This ends the recursion. All right, so with this, we can now implement our recursion in Mathematica and solve it. So I want to emphasize again, it's important to understand that this problem formulation, the decision time, and that's what the state is, the point at which a decision is made, that's the state, is just as he's ready to leave. Then comes his travel time to Lake J is t, ij. Then he fishes there for 1 hour. So we have to subtract tij from 1 from the remaining time n for the next decision time. right? We're jumping here with n minus t ij minus 1, we're jumping from state to state, from decision time to decision time. And at the same time, y of I is the amount of fish he just caught in the lake and where he's about to leave. All right, and that means he now has two choices because he just arrived at lake 1. If he fishes for 1 hour in lake 1, he gets a total of f of 11,1 fish, because after 1 hour he still has 11 hours time and he's ready to leave lake 1, so it's f of 11,1, because the next decision time is just when he's ready to leave lake 1, and that will cost him 1 hour of time, and his yield is f of 11,1. But he also has the choice to immediately leave lake 1. Maybe lake 1 is not so profitable. And in that case, he gets f of 12,1 minus y of 1 fish. So that's because he now, if he leaves immediately, he has 12 hours time remaining. But by design, we have included the catch of lake I in our recursion here. You will see that yi is added to the maximum. But when he leaves lake 1 immediately, he didn't get anything there. So that means f of 12,1 includes the catch for lake 1, which he didn't get, so we have to subtract it. So in that case, if he leaves immediately, we have to compute f of 12,1 minus y of 1, because f of 12,1 gives him credit for the catch of lake 1, which he never got because he left. Right? Note that fn of I includes the catch from lake I, but he is about to leave lake 1. So it would include the catch from lake 1, which he never got. So we have to subtract it. Okay? And these are his only two choices at the beginning. And we're interested in getting the larger one. We are interested in picking the larger one of these two choices. And that's why we compute these two here. We have to compute the larger one of these two. Either we fish there for 1 hour, then we're interested in f of 11,1, or we don't fish there for an hour. We leave immediately. Then we have f of 12,1 minus y of I. Okay, so let's initialize this. Let's compute. And here are our two choices. And here we see that in this case, with these random numbers, that it would be more profitable to start fishing at lake 1. It's not always the case. Sometimes it's better to not fish at lake 1, but leave immediately. Right? I can run this a few times, and here we have a tie. Here it's better to fish in lake 1. Here again. Here again. And here it's better to leave immediately, right? Because he catches 53 fish if he leaves immediately, and he would only get 48 fish if he starts fishing at lake 1. All right. So again, I point out that in the version above we memorize, and for large problems that is a necessity. For small problems it's not. And without memorization we can simplify this even further. We now just have a much more simplified version without the memorization and can make our computation here. All right, so that brings me to a very important application of DP, and that is production planning and production optimization. One of the central topics in operations research is the allocation of scarce resources. And linear allocation of models of vast dimensions are routinely and quickly solved with linear programming. I'm not touching on this in this session. Nonlinear models, on the other hand, of much more modest dimensions are better suited for DP. So, in the following example, we will relax the linearity restriction and allow the resource consumption as well as the profitability to be pretty much any non-negative revalued function, and we call them C and P. So C represents the consumption of a resource and P is the profit that we get by selling the commodity that we are producing with the consumption of the resources. So we'll have k units of the resource available, where k is a non-negative integer. And the resource of k units can be allocated to the production of various amounts of n different commodities. And these commodities are only produced in integer quantities, right? You can't produce 2.7 engines or 11.3 cars. So we assume we are only dealing with integers, non-negative integers. And producing x of I units of this commodity I consumes c of I of x of I units of that resource and yields us a profit of p of I of x of I. Right? Note that this allows us to model this completely non-linear. We can use whatever consumption function and whatever profit function we will want to use. And it's acceptable to leave some units k unallocated, but we cannot produce more than w units of any single commodity. So we also have a certain restriction here. So we model this in the following. So P1 of X1 plus P2 of X2. This is what we want to maximize. We want to maximize the profit. So that represents the sum of these profit functions from P1 of X1 plus P2 of X2 and so forth until we get Pn of Xn. And you will see that P is possibly totally nonlinear. It doesn't have to be linear. We can use whatever profit function we want in order to model the profit for selling commodity Xi realistically. So this shows us the restriction of the resource. We cannot consume more from the resource than what we have available. So consumption 1 of X1 plus consumption 2 of X2 plus and so forth has to be less than k. We just don't have more than k units available. And we also have the restriction that Xn itself has to be between 0 and w. We cannot produce more than w of any one given commodity that we want to sell. And our objective is total profit. And now let's start modeling this as a DP. So in our case, it's better to go backwards. We start with n units and then ending the recursion at 1 as initialization. And at every decision point, which is a state, a certain number of unused units, say y, remains available. So it follows that y is some integer quantity that satisfies y between 0 and k. So these y units now have to be allocated to the units 1 through n. So we make a definition. F of ny is the maximum total profit that can be obtained from allocating 1 unit of the resource to production of commodities 1 through n. You will realize this sounds similar to the knapsack that we had before. So through this configuration of n, k is the maximum profit for the whole allocation. So f of n, k, capital N and capital K, that's the number that we will want to compute. That's what we'll want to look at when we have set up everything correctly for the recursion. F of n, k, capital N, capital K is what we're after. This is the number for which we are setting up everything. F of n, k is the solution. So the problem has just been embedded in a family of n times k plus 1 related optimization problems, namely the determination of f of n, y for n constraints. And therefore f of n, y is attained for each n and y. So let's now develop the functional equation. We produce x units of commodity n, where we have to obey the restriction that c of n and x cannot be more than y. We just don't have more than y units available for each and every state. And production quantity x is feasible if for n, y, x is an integer between 0 and b. I think I've called this w. And the restriction c of nx less than y holds, right? Those are the restrictions that we have. If we don't have them, then we don't have a valid recursion. We cannot consume more than y in every state, where y changes with every state. And we also cannot produce more than w units per item. That was our restriction here. We need xn to be between 0 and w. So we have to restrict the entire thing here for our recursion. So when n is 1, feasibility is our only concern. So we are maximizing p1 of x, because it's the first state, and we just have to make sure that x is feasible. So for f1, y, we take the maximum of p1 of x over all the feasible x. But that's only the case for state 1. So next, we now have to let n to be larger than 1. So at least 2 commodities can be produced. And the profit obtained by producing x units of commodity n and allocating the remaining y minus cnx to produce the commodities is now, by construction, p of n plus f of n minus 1 y minus cn of x. Right? The pn, again, note that we are adding the utility that we get, the profit, to f, and submitting inside the recursion the reduction in the available capacity, that's y minus cn of x, and we are going to a previous state. So we go from n to n minus 1. Right? This is the recursion that we have to perform. We always have to go to a previous state, n minus 1, and we always have to subtract from the available resource whatever we are consuming at stage n, and that is y minus cn of x. So this is very similar to what we had before. Make some money, that's pn of x. Lose some capacity, that's y minus cn. So the utility is added to f, and we are subtracting the consumed resource from the available capacity. Very similar to what we had before. And this is the largest profit available by allocating y units of the resource to the production of commodities 1 through n, provided that one produces exactly x units of this commodity n. But this is what we want to be maximizing. So maximizing this expression over all feasible x removes this restriction, and by construction it attains f of n, y. So now we set up the recursion. F of n, y is now the maximum of the expression, consisting of adding the utility value, adding the profit, pn of x, plus the formula that we've seen before, f of n minus 1, so we go backward one state in the recursion, and y minus cn of x over all the feasible x. So for our example, we set n to be 20 items, and in Mathematica, capital N already has a symbol meaning. So I usually indicate uppercase letters with lowercase letters by doubling the lowercase letter. So in the code I'm using below, capital N is going to be double lowercase n. So that means our factory can offer 20 different products, and they all consume from the same resource. And then we set a maximum commodity limit of w equals 1000. So we cannot produce more than 1000 units per product line, and the resource maximum of 100. So that means we start with k in our initial DP, and subsequently it will always be in a recursive core. And I use random numbers for the consumption and profit factors. I just don't want to manually type in a bunch of bogus numbers. If I want to use large numbers of bogus numbers, then I use random numbers. So then we simply implement the formulas above. We compute f of capital N and capital K, and of course we memorize. Again, not necessary for small problems, but good practice, because eventually we want to solve big problems. So let's set this up and initialize this. 20 products, and we take random integers between 1 and 10 for our profit factors, and random integers between 1 and 5 for our consumption factors. 1000 is the unit limit, k is the weight limit, and we define our CIX and PIX with memorization. You see this here where we're using set delete on the left, set on the right, and x is also random numbers between 1 and n, 20 of them. So here's our recursion, and we have to split it up into 1, y and n, y. And so we need to make sure that x is between 0 and the production restriction, and we also need to make sure that our consumption is less than the resource restriction. And then we want to have p1 of x of I, and we maximize this over all the I, which go from 1 to nn, right? So this is exactly this equation here. Yes, this is the one here. f1, y is the maximum of the p1x with x feasible. That's what we have here in this line. This is for f1, y, and this is p1 of x of I here in this recursion. Now in the general, we want f of n, y. That's this equation here. And here as well, we maximize over all these possible solutions that we have, and we get them by going over all the x that are feasible. So that means I goes from 1 to n, subject to the restrictions. And again, xi has to be between 0 and the maximum production restriction, and the consumption has to be less than y. That was our resource restriction. And then it is p of n of x of I plus the f expression here. This is really this formula, no different from this formula, plus f of n minus 1 y minus cn of x. So we have this expression here. And when we have defined this, then in pretty much 0 time we can compute f of capital N and capital K. We get 257. Okay, I think this is fairly straightforward once you understand the definition of the state, where we have to go in the recursion, we have to go one step back. We wanted to start at capital N and then go down to 1, right? We go backwards, starting with n and ending recursion 1 as initialization. So we have to use the minus 1 all the time here in the recursion. We have to obey the reduction in the resource consumption. We have to make sure x is feasible, and then it's a simple recursion where we take the maximum of all these alternatives. So in the previous example, we had basically a generalization of Knapsack, right? Knapsack is just a special case of the general production system that I've shown, and it used only one resource. But we're now interested in adding more resources to our production. It's not realistic to assume that a production consumes only from one resource. So we have to be able to produce commodities that consume multiple resources. And I think it would be great if we could take the previous model and then generalize it in a simple, straightforward, logical manner that would allow us to consume multiple resources. And in the following, that's exactly what we're gonna do. We see that this is easily done conceptually, but it also entails a lot more running time. We are coming to the so-called curse of dimensionality. So I think you will understand the following very easily, but it does take a toll on the computation time, simply because we have another dimension in it. So in the following, we'll just use one more resource. So we now have two resources. And the second resource is modeled after the first. We assume that we have L units of a second resource, and now producing X units of the commodity now consumes both C of N and X units of the resource 1, just like as we had before, but additionally also D of NX units of the second resource. And as before, some resources of C and D can remain unallocated. That would be fine. So our mathematical representation is now the following. We now try to maximize over the profitability factors of all these commodities that we produce. So this is unchanged. Subject to, well, now we have one more equation, right? We have the C equation that we had before. The sum of the C's has to be less than K, but now also the sum of the D's has to be less than L. and we have the same restriction in terms of feasibility. We cannot produce more than W units of every commodity, right? Xn has to be between 0 and W. We cannot produce an infinite number of our commodities. So each Xn is restricted by 0 and W. Right, so this looks pretty much the same as we had before, except in our restriction equation, in our restriction inequalities, we now have also a restriction on D. The difference to the previous problem formulation is only that we now have an additional constraint, but that will increase computation time significantly. And now the new question becomes, what constitutes a state? Just what is a state here? Now we have Y units of the first resource remaining and Z units of the second unit of the second resource remaining. And that is true for every decision point, for every state. And the allocation of these resource units can be done without knowing or considering the other production levels. We really need to have some independence here. That means we now have to consider the triplet N, Y, Z as our state. Before we only had N and Y. We now have N, Y, Z. Because we have another restriction here, we introduce Z in that. So conceptually, the situation is just as it was in the previous example. The production level X is now feasible in the state N, Y, Z. And it now has to satisfy both Cn of X less than Y and Dn of X has to be less than or equal to Z. And this is W. I'm using W, not B. So similar to what we had before, we get the following functional equation for n larger than 1. We now have a third argument in f. We have n minus 1 as we had before, because we're moving backwards in stages from capital N down to 1. We have to subtract the consumption Cn of x from y, but we also have to subtract consumption dn of x from, this has to be a z. This has to be a z, sorry. And we're adding our profit P on top of our f, and that gives us f of n, y, z. All right. So you see this is the same as we had before, except on the left side we have a third argument z, and on the right hand side we also need to have the third argument z minus dn of x. And for n equals 1, we also have very simple, we have f of y, f of 1, y, z being the max of p1 of x over the feasible x. So this is as we had before, except that x now has another restriction to be feasible. We have another restriction to obey. It reads the same, x is feasible, but in order to have it feasible, there's another restriction to obey. It's very easy notation, just say x is feasible. But what makes it feasible now actually has changed because we have another restriction. So the right-hand side looks no different from the initialization in the previous example, but we have to ensure that x feasible now also obeys the restriction on D, not just C. So with that, we have our code like this. Let's produce 15 items. We have profit factors and we have now consumption factors, one for C and one for D. And we have a production limit of 10,000. We have K units for resource 1 and we have L units of resource 2. So we define our consumption C, consumption D, our profit P, and our X continues to go all the way up to N, in this case 15. So here are our equations. The first one is for 1, y, z, and the second one is for n, y, z. So we have to initialize these recursion equations, and you will see that we have for the feasibility restriction, we also have D now as a restriction, right? We had x between 0 and w as before, we had c less than y as before, but we now also need d less than z, and we have the same in the general recursion equation, not just for 1. Here's the same, x between 0 and w, we have c less than y, we have d less than z. Okay, so now let's compute our optimal value for f of capital N, capital K, capital L, and you will see that this takes a significantly longer amount of time. That's because we have L plus 1 additional multiplications. That's because we have L plus 1 additional iterations that we have in our recursion here. So this can easily take, I think, half a minute or so, but then we have computed our solution using 2 resources. I think that is a valid generalization, and as I said, conceptually it's really not much differently, but it takes so much longer because we have a much bigger recursion going on. And you see how long it took for the computation of f of nkl compared to the memorized form in the table, right? This here was pretty quick. Once we have it, that's the advantage of the memorization. Once we have computed f of nkl, then we are ready and we can just look it up for the whole table. All right. So here's an important observation. Introducing a second type of resource poses no conceptual difficulty. The number of states, however, has grown by a factor of L plus 1. So before we had states n, y, and now our states are triplets n, y, z. So our recursions require one maximization or minimization per state, and the computational work increases roughly proportionally with the number of states. And if we were to introduce a third resource m, then the computational effort would increase by a factor of m plus 1, and we would get quadruple states. So we encounter this, and it is called the curse of dimensionality, which is a common problem in DP. Alright, so as I had promised, we're gonna look at multiple optimal solutions in more detail. This is an important item if you're interested in finding all your optimal solutions and not just one that satisfies the formal restrictions or the formal project configuration. So if you're interested in finding all of the optimal solutions, things get a little bit more challenging. I had already mentioned the cheat on the arc length method in the 4 hikers problem. Right? And this is definitely not elegant, and it also means that you already have to know at which node you get more than one solution. And I think it was node number 7. We kind of knew it, we also saw it from the output, but in general, you don't always know which node has more than one solution. So in the following, I'll show you how to find those out. And another way, although it's not guaranteed to work, to show all the solutions, it gives you at most 2, is to simply run both recursive fixing and reaching. If the computation takes the time, then you can run them in parallel, right? We have great parallelism features in Mathematica. You can run recursive fixing in one subkernel, and you can run reaching in the other subkernel. So the computation times will be about the same. Not always. There can be very imbalanced problems. There can be recursive fixing taking much longer than reaching, or the other way around. It's not a guarantee, but still, they're independent tasks, and if they're independent tasks, they can run in parallel. So this approach using both recursive fixing and reaching gave us 2 solutions in example 3, but it did not provide multiple solutions in the 4 hikers problem. And it's not guaranteed to work, and you may have more than 2 solutions. So I think it's a good first step, but it's also not a guarantee to give you everything. In fact, it may not even give you both. It may result in the same solution being output, and you still have multiple solutions. So for most real-life data, non-unique solutions are rare. And that can really only happen if you have integers on small graphs. But that's what we used above. We mostly had integers on small graphs. So that's why I think one method is to simply compute as above, but then use recursive fixing and reaching functions with a modification of the outputs that are the results of the minimal by and maximal by computation. If there's always just one element, your solution is unique at that step, not for the overall problem, but at that step, because we had a minimal by and maximal by at every state, at every decision point. So let's look at how many elements we get in the list returned by them. So let's modify our recursive fixing and our reaching a bit. And instead of just proceeding with a variable that I called temp that we are appending to the tree, let's print it, right? Let's intercept it first, print it, and then proceed as we did before. We took the first of the minimal by or maxima by and appended that to the tree and used that temporary variable here in our minimization or maximization for f. So let's first intercept it, print it, then take the first of it and proceed as usual. From this part on, it's totally as usual. It was the first of temp, but let's first print it here. So with these initializations, let's look at our 4 hikers on a bridge problem. So I'm showing the net once more here. So I redefine the net again here, and let's look at recursive fixing, and we see that we have 3 nodes where we have 2 solutions, and with reaching we also have 3 nodes where we have 2 solutions. So with recursive fixing we have 3 nodes with non-unique values, and it's the left indices that are the same, right? It's 913 and 915. The next one is 813, 814, and the third one is 710, 711. So it's the left indices that are 9, 8, and 7. And given that this is recursive fixing, that tells you that there are other paths that attain the same solution values from the source to nodes 9, 8, 7. And also take note of the fact that not all of them are on the full path from the source to the sink. Only 7 is. 9 and 8 are not. So this is only the case for one of them, that's 7. The other 2 also provide for non-unique solutions, but they are not on the full source sink path. And with reaching we have 814, 1014, we have 915, 1015, and 1216, 1316. That means from nodes 14, 15, 16 onwards towards the sink we have multiple paths. And here as well only 1 is on the source sink path. The other 2 are on path branches that are not on the full source sink path. So that's good news and bad news. It's good news in that they are not affecting your solution. And the hikers on a bridge was an example where you needed the full path from source to sink. You were not interested in anything in between. So that's the good news here. When you have lack of uniqueness, then in 2 of these 3 cases, it doesn't matter. So at least that would tell you which nodes to inspect closer. You know exactly which ones they are. It's 9, 8, 7 for recursive fixing and 14, 15, 16 for reaching. And another solution is using random choice instead of first and then running it several times. Right? So here instead of first we use random choice. And this may seem awkward, but keep in mind that DP is very efficient here. We are running in O of M. So multiple runs should not be too expensive. Now, of course, if you have a really big problem of multiple dimensions, as above for the generalization of Knapsack, we had restriction K, L, and M, right? So now it was a quadruple state definition. This will not always work, but if it does work, you have a very efficient setup for the DP recursion, then this really shouldn't be a big problem. And in the following, I'm going to show you that it really is easy enough for this short problem that we have here. So let's use random choice instead of first for recursive fixing. Let's run it 1,000 times. And I set up a collector variable collect, and I'm appending to collect the pair that consists of tree and f. Okay, it took 4 seconds for 1,000 runs. Let's look at the unique solutions of that, and we have 8. We get 8 unique solutions that we now want to look closer at. And given that I get 8 outputs and they are fairly big each, I have split this up into 4 rows of 2. And if you look closely, they may look similar, but they're not. You can clearly see that the one with the 60 is here at the right edge of the first one, somewhere in the middle here. If you look closely, they all are different. I think it's easy to see for the first 6. The last 2 are a little bit trickier to see, but if you look closely, here we're going 1, 7, 10, and here we're going 1, 7, 11. Right? That was exactly the 2 paths that we had seen earlier on, where I was fudging the data by calling 10 to be a 9.99999. That was also the distinction, 1, 7, 10 versus 1, 7, 11. Other than that, these graphs are the same here, these 2. So all these 8 graphs are different if you look closer at them. We do the same with reaching. Instead of first we say random choice, let's define it. Let's run it 1,000 times. Should also take less than 4 seconds, something like that, 3.6 seconds. Let's collect the unique ones. It's 8 that are unique, and let's plot the graphs. And again, it's 4 rows of 2. If I made them any smaller, then we couldn't really see anything in them. And again, if we look closely, we will find out that all these 8 graphs of shortest paths trees are different. They are different. They all have the 60 and the 22 node at the bottom, but all these 8 graphs are different. So these are the 8 solutions that we have there. And here again, you can see we have 1, 7, 10 down to 22, and here we have 1, 7, 11 down to 22. Okay, so we have 2 different solutions, and we have that out of 8 total solutions. Okay, next let's revisit the minimum maximum segment altitude path example. So let's look at the net again. Let's plot it again. You will recognize this graph structure. And let's also do the same thing here. Let's first look at the print for recursive fixing, the print for reaching, and let's run them. Recursive fixing, we have 2 solutions here, and with reaching we have 2 solutions here. Okay, so that would at least tell us where we have to look at, right? Here we have 1, 2, 1, 3. So 1 is the node we would have to look at closer. Here we have 4, 8, 6, 8. So 8 is the one that we would have to look at closer. So let's now Monte Carlo them. You see the random choice here. Let's run it 1,000 times. This is a bit smaller. This runs faster. And we have 2 unique solutions. So let's show them. And we can see that we have 2 unique solutions. We have 1, 2, 4, and here we have 1, 3, 4. 2 valid solutions. Same with reaching, random choice, run it 1,000 times, collect the unique ones, let's plot them, and here as well. We have different trees as output, but we don't have different optimal paths. Here we have 1, 3, 4, 5, 7, 9, and here as well 1, 3, 4, 5, 7, 9. So with reaching, we didn't get 2 solutions. With recursive fixing, we did. All right. So I'm now writing a bit of a conclusion on multiple solutions. So when textbooks present algorithms in combinatorial optimization, then they typically guarantee only a tree, one correct optimal solution, and not all of them. And that will be entirely sufficient in many cases. Oftentimes people just want one valid solution and get on with life. As long as they have one, they don't care about the others. They just have one. It fulfills the task. It meets the objective. So one is all we were interested in. But for many real-life applications, it's usually also the case that many factors were not included in the model. We just cannot include everything and optimize down to the last level. And this can be because they cannot be quantified. There would be no data for them, or they would complicate the model so much that it's easier to just drop them and perhaps rely on getting multiple solutions. They may increase complexity and computation costs, and something like a $3 bus ticket will simply be ignored. Any model is only correct to the extent that it was specified correctly, and therefore many items have to be dropped from consideration, and oftentimes that's just entirely justified. And in many cases, such as the lack of quantifiability is really of important concern, and sometimes it is not. That doesn't mean the models are worthless, but they don't answer the management questions completely. There are many things that just cannot be quantified and therefore cannot be included in the model. For example, things like customer satisfaction, employee satisfaction, or the hotel costs for layovers of airline staff, interest expense, risk, taxi expenses for local transportation, corporate image, how do you quantify that, right? Long-term effects, pollution, trash, garbage, waste management, political uncertainty. So the list is endless. But if you have multiple solutions, then you can now pick and choose which one may fit in better with your secondary objectives. So one way out of this is to look at several solutions that attain the same objective value and then pick the best solution from the possible alternatives based on another concern that was not included in the model. For example, let's deplete our inventory from warehouse 1 faster than from warehouse 2 because the air conditioning in warehouse 1 doesn't work well and it's already June. Okay, so this was not modeled, but we have 2 or more choices. So now we can say, for example, okay, let's try to make warehouse 1 NT faster than warehouse 2 because we have an air conditioning concern that we didn't model. It's generally good to have choices even among the optimal solutions. And the secondary concern can also be the path length itself. In example 3, we saw that one of the optimal solutions is shorter. We had 1, 2, 6, 7, 9, 11 as one solution, and the other one was 1, 3, 7, 9, 11. So that one only has a length of 5, the other one has a length of 6. So just because they have the same length doesn't mean they're really equally preferable. What if a driver wants to minimize the number of overnight stops? Then he would pick the solution that has only 5 nodes. What if an airline passenger wants to minimize the number of plane changes? Also, cargo should not be unloaded and reloaded too many times, so the number of stops would really be a valid secondary concern. It may be done if it saves a lot of money, but if the 2 solutions give the same optimal value, then you may prefer the one that doesn't have so many hops in between them, not so many plane changes or cargo loading and unloading. So a lower number of stops would be a good secondary concern. So what if the driver of our beat-up car doesn't want to drive too far to the south because southern latitudes are usually hotter than northern latitudes? Again, not modeled, that was not part of our model. But when we have multiple solutions, he now has a choice. He could, for example, drive around the Rockies to the north, Wyoming, that would probably get him through Wyoming and Utah, and he can prefer passing the Rockies to the south, that would be New Mexico, right? Something like Albuquerque, Santa Fe. What if solution A would get bad press in the media and solution B would not? Maybe solution B would even get praise. So when product choices have the same optimal value, management can select the appropriate choice based on secondary concerns. That's why I think it's important to look at multiple optimal solutions. Not just take one of them, the one that the algorithm happens to spit out and then run with it, but instead look at the entire spectrum of optimal solutions that you may have. All right, so that brings me somewhat towards the end. I want to point out that there is so many applications of dynamic programming. Here I'm just listing those that I personally have met in my life, and there are many more at this hyperlink. This is a Wikipedia page and there are just so many examples listed. We have algorithms that use dynamic programming. Have a look at this Wikipedia page and it will convince you that DP is incredibly powerful, incredibly efficient, incredibly code efficient, and that many problems can be modeled as DP problems. DP definitely has problems itself, but in the end, many problems are still best modeled as DP. Okay, that brings me to my final comments on dynamic programming. I hope I've made clear that it's definitely a strength of DP that it is easy to set up once the problem is fully understood and the recursion is clear. That is important to do. That is an important requirement. But if you have that, then it's very easy to understand and very easy to solve. It makes for incredible code efficiency and simplicity, yet you get very powerful and flexible computation of results. On the other hand, there's the curse of dimensionality, which can be, in a way, I think, seen as the price of generality. DP is so general, so flexible, and I think the curse of dimensionality is a bit the price of this generality, this big flexibility that you have in modeling with DP. I want to emphasize dynamic program is not necessarily the most efficient way to solve specific combinatorial problems, but it is the most general other than branch and bound. Branch and bound is the most flexible, but is also terribly inefficient. It's the very last resort. If you have absolutely no other idea, branch and bound is the method you would use, you would have to use, and you should try to avoid branch and bound at all cost. But that's not to say that DP is always efficient. It definitely is not. The recursive fixing of the first examples were about the most efficient ways to solve the problem, because we had exactly one and only one evaluation per arc, and adding t from I to j here represented as net of hash and fj, and comparing the sum with the best f of I so far. That means we are consuming linear time. This was O of m. You should understand you can't expect anything more efficient, provided that the arc lengths are unrelated in length. Then we get O of m time, right? Sometimes that's not the case. Sometimes the arc lengths are related with each other in a certain relationship. They may not be totally independent. But if they are, then this is really the fastest way to do that. Unfortunately, dynamic programming usually doesn't lend itself for parallelism. Most algorithms in DP are inherently single-threaded. However, it is possible to run multiple variations of the algorithm in parallel. As I had mentioned, recursive fixing versus reaching are some of these applications. The modifications between recursive fixing and reaching are minimal. So if you run them in parallel, you get at least the following two advantages. You get a cross-check if you have implemented a bug, because if the optimal values are not the same, then you've made a mistake somewhere. Always good to run a second version in parallel. It costs you no extra computation time. The modifications are minimal. It's always good to cross-check if the end result that you get really is correct, or if you may have made a mistake with something. And it has the potential to find you two solutions if there are multiple solutions, but that's not a guarantee. Even when you run recursive fixing and reaching, you're not guaranteed to find two or more solutions, even if there are two or more solutions. So next, I want to point out that DP can only be done easily for the computation of the values of the optimal solution. They often don't provide the solutions themselves. And that would involve much more algorithmic work, for example in palindromic substring or trout poaching. On the positive flip side of this, these algorithms are so simple that can even be implemented in C easily and then called from Mathematica with library link. Palindrome and trout poaching could easily be converted to C. It was very simple code, and then running these algorithms with library link would make them even faster. I'm generally not a friend of writing complicated things in C. I will always prefer Mathematica for that. But short, simple algorithms with simple data structures can easily be done in C and then called with library link. And when I say simple algorithms with simple data structure, well, what comes to mind, this is pretty much DP due to the simplicity and code efficiency of the recursion, right? When I hear simple algorithms with simple data structures, I immediately think DP, so that's what this whole session is about. I briefly mentioned that Dijkstra is a modification of the dynamic programming approach for shortest path. It has the advantage that we can now allow for cycles. And in all our examples above, we required that the graph is acyclic. Dijkstra does not impose that restriction, but it also comes at the disadvantage that we can now no longer allow negative arc lengths. So you gain the ability to handle problems with cycles, and you pay for that with the restriction that you can only have non-negative arcs. And moreover, Dijkstra needs additional data structures, lists and sets, and that makes the algorithm a bit more complicated than simply looping over simple, intuitive, straightforward recursion. That's really the Bellman equation, the principle of optimality. In the end, even Dijkstra is still DP. It's the shortest path with modification. Related to that, Dijkstra and both Floyd-Warshall, and for Floyd-Warshall I refer to the previous session about library link, they can be understood as DP algorithms. They both use the principle of optimality. So Floyd-Warshall is pure DP in that it computes the all pairs shortest path, that means from all nodes to all nodes. And with our DP approach, we don't have all pairs. We can always have only one source and one sink. With Floyd-Warshall, you can use any node as source and any node as sink. It's generally the best way to solve the all pairs shortest path problem. There are Floyd-Warshall variations that use parallelism, but they get much more complicated, and I think the gain is really not terrific. An alternative approach to all pairs is simply to take the one source method shown above and let it run in parallel with all the nodes as starting nodes. So we would do what we've done above here, except we pick multiple start nodes and end nodes and run the whole thing in parallel. That is coming close to Floyd-Warshall, provided you have a lot of CPUs, a lot of cores that can run in parallel. Next, I recommend you use some smart pre-processing. For example, if you're looking to minimize, then arc lengths of infinity should be eliminated before we even start the algorithms. And oftentimes, lengths of infinity or minus infinity are used to indicate that there is no way to get from I and j directly. So where we used arcs in our display at the beginning, then there was simply an arc that was shown as an arrow with an arc length with it. And when there's no way to get from I to j, then the nodes simply don't have an arc. Well, if you use the full matrix approach, then you would have to model this as infinity or minus infinity. So they can never be in an optimal solution, but that's a way that allows you to model them with infinity, minus infinity. They can never be in an optimal solution, so you could throw them out from the beginning. Why iterate over such arcs and loops? So try to decrease your data size, be parsimonious, throw out stuff that you don't need. Same with maximization. And next, related to the previous point, in a dense graph or network, that means a network in which every node is connected with every other node. In graph theory, that's called a complete graph. The efficiency increasing restriction to only look at the outgoing arcs for a given node, and a recursive fixing in reaching that would be only looking at the incoming arcs for a given node, that can be replaced with the use of an n by n matrix that contains the cost for all the arcs. And this may make things a bit easier algorithmically. The algorithm gets even shorter now because we can use simple matrices or tables or arrays, but now the running time is longer than all of them. We are no longer linear, we are now quadratic. And here you cannot throw out infinity and minus infinity. You have to keep them in order to model that there are no arcs, no connections between nodes I and j. So here you have to keep them in. So you have much bigger matrices, including possibly infinity and minus infinity, but the code is getting a little bit shorter. So the linear running time of O of M is inherently relying on the use of adjacency lists, and you remember this with minimal by and maximal by. In graph theory, then that would be called adjacency lists. If the graph is not quite full, you can use infinity or minus infinity to indicate there is no direct link between the nodes and still use the algorithmic simplicity of these two blocks that I'm showing you here. So the algorithm then for recursive fixing would simply be this two-dimensional do loop. You set the node indices to 0 and you set it to infinity for the j's. Then you can go over this loop and you have Vj as the minimum of Vj and Vi plus the travel from I to j. And for reaching, you see that this is exactly the same thing, except the order of the two loops is reversed. You now have I as the outer loop and you have j as the inner loop. Here for recursive fixing, you had j as the outer loop, I as the inner loop. Right? These two above are the same, except that do loops are interchanged. I still think you should try to avoid this. Use adjacency lists instead. It's more efficient if you can do it that way. But if you have a dense graph or dense network, then it's easier, it's simpler to do that with these full arrays rather than using adjacency lists. But your runtime comes up. So I want to emphasize again, it's incredibly fast. So if we look at the 22 node suspension bridge example, let's initialize this net again, recursive fixing. Let's look at the time. It took 6.81 milliseconds for the whole computation. That means an average time per node, so I'm dividing by 22, would be 0.3 milliseconds. And the average per arc, so I'm dividing by 48 because we have 48 arcs, would be 0.14 milliseconds, right? Think about an algorithm that computes the optimum in 6.8 milliseconds. I think this is incredibly fast. I personally find it mind-boggling how simple and fast it is. So let's take a bigger example, the 1000 item and 500 weight units knapsack example that we had above. So let's set a size of 1000, a capacity of 500. Let's compute it and evaluate the runtime. The whole thing takes 5.4 seconds, right? 5,400 milliseconds. That means the average time per item, so now I'm dividing by size, and that was 1000, was 5.4 milliseconds. And the average per weight unit that we looped over is now this time divided by capacity, which was 500, so that's 10.8 milliseconds, right? I think these are absolutely reasonable numbers, and we don't use any parallelism. We don't use a GPU here. This is all on a CPU. I just want to emphasize that this can be incredibly efficient and super fast. And my final point is I want to point out the Mathematica feature that associations behave very similar to indexed arrays and lists. If a variable is to be used as an indexed array, you merely need to declare it as an empty association before filling it with data. And now it will be used as an association without any further code changes, right? So let me show this with I think this was the first example that we used. And note that here I have commented out f equals empty association, right? So let's run it and look at f, and we see that we have an indexed array here. F of 1 was 19, so this was the very first example. But if I do initialize f to be an association and run it again, we are getting the same result, but here f is now an association. So I want to emphasize the point that associations and lists are so similar in terms of its treatment and manipulation, in terms of lookups, in terms of filling it, in terms of length and mapping. It is a very similar treatment when you want to use them for lookups or for the construction. And in order to turn what would be a list into an association, all you need to do is initialize it as the empty association and then put numbers in it. Then just fill it with new numbers. Then you will get it association. If you leave it out, then you will get it as an indexed array. That's not bad either. This is how it has been done before we got the associations. But I think this entire switch of the data type with a simple initialization with an empty association is incredibly powerful and simple. And that means that code that was written for lists can now be used on associations and vice versa. Okay, that brings me at the end of my session for today. I hope you had as much fun as I had. I hope I see you next time. Thank you. Bye bye.